Welcome to Hot Chips 34. Tutorial 1. CXL.
Greetings, everyone. Welcome back to Hot Chips. I want to give a shout out to the organizing committee for the incredible work they do in bringing this conference together. My name is Nathan Kalyanasundharam from AMD, and I'm here representing CXL today. The first tutorial session is going to be on CXL. A very quick background for those who are new to CXL. CXL is an industry consortium comprising of over 200 companies. And the primary focus is cache coherent interconnect and related technologies. Earlier this month, CXL Consortium released the CXL3 specification. CXL3 enhances the node level capabilities and took a big step to enable rack level memory fabric. Senior architects from many of our member companies have done incredible work to bring this technology recently. Some of them, you're going to hear from them today. And just before we begin, I want to go over some logistics. So please use the Slack channels to ask the questions. There will be a live Q&A at the end of each session. All the sessions are focused on specifications and not on products. So just please keep that in mind when you ask your questions. So for the first tutorial session focuses on overview and evolution of CXL and is led by Ishwar Agarwal. Ishwar is a senior principal engineer at Intel. He is responsible for data center processor architecture. Prior to Intel, he worked at Microsoft in Azure Hardware Architecture Organization. Ishwar specializes in CPU architecture in the domain of I/O, memory, coherency, and interconnects. Ishwar has also served as the co-chair of the CXL Technical Task Force. Let's get started with session 1.
Hello, my name is Ishwar Agarwal. I'm a senior principal engineer at Intel Corporation, and I recently served as the co-chair of the CXL Technical Task Force. Today, I will be presenting CXL overview and evolution. CXL, or the Compute Express Link, is a consortium of 180 plus member companies with a board of directors comprising of hyperscalers, CPU vendors, IP vendors, software providers, etc. The CXL specification is delivered as an industry open standard for high-speed communications. So now we start getting into CXL 3.0 and understanding a brief history of the spec evolution. As you can see, the spec has undergone a number of revisions in a relatively short period of time. We incorporated back in September 2019 with the CXL 1.1 specification was released. About a year later, the CXL 2.0 spec was released. And now we are into Q3 of 2022, and we have just announced the release of the CXL 3.0 specification. The relatively quick cadence that is being seen on this timeline over here is indicative of the fact that there were so many different usages as well as different needs that the member companies brought into the consortium that led to the quick evolution of the spec. We expect this cadence to slow down as the spec matures and become more in line with the PCIe spec release timeline going forward. So what's CXL? CXL is a high-speed, efficient interconnect between CPU, memory, as well as accelerators. CXL builds upon and leverages PCIe electricals and PCIe physicals. and builds on top of it to provide memory coherency between CPU memory space and any memory that may be located on a CXL attached device. And when you have memory located on a CXL attached device, as well as you introduce the concept of cache coherency and memory coherency, you now have the possibilities of cache coherent accelerators that CXL supports, as well as devices that are purely memory devices for the purpose of things like memory disaggregation, memory pooling, memory sharing, things like persistent memory, as well as emerging memory media. The whole CXL specification is delivered as an open industry standard through the CXL consortium. And now we are on our third generation of CXL, which we call CXL3.0, which is fully backward compatible with previous generations of CXL. The future generations of CXL will continue to innovate to meet industry requirements and maintain backward compatibility as well. To talk a little bit more about what CXL is and how it looks like at the board level, this picture on the right-hand side helps us visualize this a little bit better. So in this particular picture, what we show is the common infrastructure that is leveraged by CXL. So in this particular case, imagine that there is a bi-16 connector, a PCIe bi-16 connector that's on the board. And on this bi-16 connector, one can plug in a standard PCIe card like we do today, or one can also plug in a standard CXL card, and the connector will accept both. And the reason it does so is because the connector and the interface between the connector and the CPU are PCIe electricals and PCIe physicals. And CXL runs on top of PCIe electricals and PCIe physicals. It allows the CPU to design a port on the CPU that can auto-negotiate with this particular connector and the card that's plugged into the connector to support either PCIe or CXL. When we designed CXL 2.0 and CXL 1.1, we aligned them to PCIe Gen 5 speeds, transfer rates. That means they were running at 32 gigatransfers per second. With CXL 3.0, we have aligned it to PCIe Gen 6 transfer rates of 64 gigatransfers per second. So to understand the CXL specification a bit better, we need to understand the protocols that CXL employs. And these three protocols are called the CXL.io protocol, the CXL.cache protocol, and the CXL.mem protocol. All of these protocols are dynamically multiplexed onto the same physical link. And the dynamic multiplexing of the three protocols in the same physical link happen at the physical layer, at the PCIe physical layer. This particular picture shows how this takes place at a high level through an example. So in this example, on the left-hand side, we have a host CPU, and on the right-hand side, we have a CXL device with some memory attached to it, the one that is colored in blue. The host CPU also has memory attached to it, that's one colored in peach. The CXL.io protocol is used for things which are primarily PCIe in nature. For example, the discovery of the device, configuration register settings, interrupts, DMAs, virtualization, etc. The CXL.cache protocol is used by the device to maintain a cache coherent device, a cache coherent cache on the device itself. And this is for when the device wants to access host attached memory and keep copies of host attached memory in a cache that is located on the device. On the other hand, CXL.mem is used by the CPU to access device attached memory coherently. So for example, the CPU core can do loads and stores to the blue region, which is device attached memory, in a manner very similar to how the CPU core does loads and stores to host attached memory. These protocols, the CXL.cache protocol, the CXL.mem protocol, and the CXL.io protocol have very distinct usages as we saw in the previous slide. What's interesting to note is that the CXL.cache protocol and the CXL.mem protocol are the ones that carry cache coherent transactions. And with cache coherency comes sensitivity to latency. To minimize the latency through the CXL.cache protocol and the CXL.mem protocol, we separated these protocols into their own independent transaction and link layer. The cache and the mem link layers sit on the side of the CXL.io transaction and link layer, and they operate independent of the CXL.io transaction and link layer. And all of these three protocols get dynamically multiplexed to go on the same link. When you have a PCIe card plugged in onto the connector instead of a CXL card, then through auto negotiation, the host can choose to use the PCIe stack as opposed to the CXL stack. Notice that all of these different protocols, whether it's PCIe, CXL.io, CXL.cache, or CXL.mem, they go through the same exact PCIe log file and these PCIe SerDes. Okay. So now that we have a basic understanding of the protocols of CXL, now we see how we use these three protocols. And at high level, the CXL specification has three classifications that it uses for distinct usages. And for these three classifications, it classifies devices into three types: type 1, type 2, and type 3. A type 1 and type 2 devices are really accelerators. And a type 1 device is an accelerator that primarily maintains a cache, an onboard cache that is coherent with the CPU. And so for this reason, the type 1 device only uses the CXL.io protocol and the CXL.cache protocol. An example of such a device would be, let's say, a PGAS NIC that wants to do atomic transactions to the host and wants to build the atomic engine within the NIC itself. A CXL type 2 device is similar, except that it has memory attached to the device. So in this example, we have an accelerator with some high bandwidth memory attached to it, right? And in this particular case, the HBM memory attached to the device can be accessed coherently by the CPU using the CXL.mem protocol. And examples of such devices are devices that want high throughput to the device attached memory, for example, GPUs, or dense computation accelerators such as FPGAs. And finally, we come to type 3 device, which is not an accelerator at all. In fact, it's something akin to a custom memory controller using the CXL protocol. And this memory controller doesn't need the .cache protocol, so it only uses the .io and the .mem protocol. And you would use a custom memory controller for all kinds of memory usages, such as CXL attached memory bandwidth expansion, memory capacity expansion. CXL provides a layer of abstraction so that you can have emerging media, including storage class media and persistent media, that can be added to the system. One thing to note is that regardless of the type of device, the CXL.io protocol is needed for all three types of device. Okay. So now we start talking about CXL 3.0 and the factors that are driving the need for CXL 3.0. So some of them are really nothing but industry trends that we are familiar with. For example, the emergence of high-speed, high-performance accelerators, the improvement in system memory capacity and bandwidth, the emergence and proliferation of things like smart NICs. The CPU cores themselves are becoming more and more capable, which lead them to require higher and higher memory capacity as well as higher memory bandwidth. And once you have provisioned the system with additional memory capacity, additional memory bandwidth, you have also provisioned the system with enabling it with high-speed NICs, high-speed accelerators. The next challenge is efficient data movement across memory, CPU, accelerators, NICs, etc. And for that, you need to have efficient peer-to-peer movement and messaging across different domains. And finally, memory continues to become or to be a bottleneck for system performance, both in terms of memory bandwidth and memory capacity. So with CXL 3.0, we double the bandwidth over previous CXL generations. And we do so without adding any latency over previous CXL generation. We introduced for the very first time Fabric capabilities in CXL 3.0. So things like multi-headed devices, Fabric attached devices, the management of such devices, and how we use such devices to compose disaggregated infrastructure. We improved the capability and address a number of limitations of previous generations. We enhanced memory pooling. We introduced things like multi-level switching, new symmetric memory coherency capabilities, as well as more formalized, improved software capabilities. I want to emphasize with this particular slide that CXL 3.0 is a major step function for the CXL consortium. We have doubled the bandwidth. We have introduced Fabric capabilities. We have not added any latency. And most importantly, we have maintained full backward compatibility with prior generations. This chart over here shows a little bit of a summary of the evolution of major features over CXL generations. So 1.1, which was the very first rev of CXL, was introduced back in 2019. And that specification aligned with a 32 gigatransfer per second data rate with a 68 byte FLIT. And that's when we introduced the Type 1, Type 2, and Type 3 devices. With CXL 2.0, the spec matured quite a bit. We introduced for the first time concepts of memory pooling, support for persistent memory, link security, as well as first-level switching. But as our member companies' needs and usages grew, we knew that we couldn't stop there. So with 3.0, not only have we doubled the transfer rate to align more with PCIe Gen 6, we have also introduced a number of new capabilities, and we'll touch upon some of these capabilities in this overview, and some of these will be talked about in more detail in the next few sessions. So the big ones, just to highlight them for this particular slide, are things like multi-level switching, direct peer-to-peer, enhanced coherency, memory sharing, and fabrics. So we start with how we double the bandwidth while maintaining the same latency in CXL 3.0. So the first thing we note is that CXL 3.0 uses PCIe Gen 6 physicals with a 64 gigatransfers per second interface. And just like PCIe, CXL uses a PAM4 signaling, and the high bit error rate is mitigated by a scheme very similar to what PCIe uses, which uses a lightweight FEC and a strong CRC. And CXL went one step beyond what PCIe did in terms of how the CRC was defined, and I'll talk about it a little bit more. To do that, let's look at the picture on the right-hand side. So on the top, we have a PCIe 6.0 FLIT layout. And as you can see with the picture in the middle, CXL uses a 256 byte standard FLIT layout that looks pretty similar to the one above, with some differentiation in where the FLIT header sits. And that's what we call a standard 256 byte FLIT. But CXL also introduced something called a latency optimized 256 byte FLIT. And in this latency optimized 256 byte FLIT, what we do is we split the CRC into two 128 byte halves, such that we send 6 bytes of CRC with each 128 byte half. What this does is that it mitigates the store and forward latency at the receiver and results in a latency saving of 2 to 5 nanoseconds, depending on your link width. This scheme of how we do the FLIT manipulation extends even to lower data rates. That means the 256 byte FLIT can be used over previous generation data rates. That means it can run over 32 gig data rates, 16 gig, or 8 gig. And the fact that we move to this 256 byte FLIT provides us a whole bunch of real estate that can be used for a number of protocol enhancements that we introduced with CXL 3.0. So before we get into those protocol enhancements, wanted to do a little bit of a summary of what CXL 2.0 was in order for us to be able to understand where 3.0 is going. So the first thing I wanted to talk a little bit about was the concept of memory pooling, which was first introduced with CXL 2.0. So what this picture shows us is that we could construct with CXL 2.0 a system that comprises of multiple hosts. In this picture, those are labeled H1 through H hash, right? And these hosts could then be connected to a multitude of devices, D1 through D hash. And what can be done with memory pooling is that when you have memory attached to these devices, the Ds, these memory regions can then be subdivided into fine-grained chunks that can be assigned to different hosts at different times. And this concept of being able to take a region of memory and be able to slice and dice it dynamically and assign them to multiple hosts is called pooling. The reason why pooling is so interesting to system designers such as myself is that it allows for memory to become a more fungible resource. No longer is memory something that needs to be pre-provisioned statically and hard tied to a host. It can become something that is allocatable based upon system requirements at runtime. And for this to work, CXL 2.0 defined this concept of a multi-logical device, which allowed for fine-grained memory allocation. The thing to note over here is that memory pooling allows us to slice and dice memory and then allocate that memory to a given host at a given time. That means a single slice can only be assigned to one host at any given time max. It cannot be assigned to more than one host. And with CXL 2.0, we also introduced for the first time the capability to have a switch. So we formally defined the concept of a CXL 2.0 switch. However, it was limited to a single level of switching. The reason the switch was interesting for CXL 2.0 was that it allowed for memory expansion and resource allocation. What this basically means is, as we saw in the previous slide, we could use the CXL 2.0 switch as an intermediary that would allow us to do memory allocation to different hosts at different time. It also allowed us to build fan-out systems with a single level of switching. So the CXL 2.0 switching solution was great, but there were two limitations of that particular solution. The first limitation was that it only supported a single level of switching, right? You could not build multiple level fan-out switches. The second limitation of a CXL 2.0 switch was that we could attach a max of one type 1 or type 2 device below a single CXL root port. So in this particular picture, we could not have more than one type 1 or type 2 devices below this switch's downstream ports. With CXL 3.0, we fixed both of those limitations. Right? So what we did was we defined CXL switching to be multi-level and thus cascades, and supports now a much greater fan-out of devices that can be attached to CXL. And we also fixed the second limitation of allowing for multiple type 1 devices to be attached to a single CXL root port. The next thing I want to talk about are some protocol enhancements that we did in CXL 3.0 for efficient device-to-device connectivity. So CXL 3.0 defines something called a virtual hierarchy of devices. A virtual hierarchy is nothing but a composable infrastructure comprising of a host and certain number of devices that are allocated to that host. So in this picture, H2 is a host, and the H2 host has been allocated devices D1, D2, D5, D6, for example. Now, what CXL 3.0 allows us to do, it allows us to have these devices talk directly to each other using peer-to-peer mechanisms, and you can have direct peer-to-peer access to coherent memory located behind any of these devices without having that request bounce off the host. That means the devices can directly talk to each other. An example of where that is useful would be, for example, let's say D1 is a NIC, and let's say D6 is a memory buffer, and the NIC wants to do DMAs to this memory buffer. Now, traditionally, all of those requests would have to first go from the NIC to the host, which would then bounce that request back to the memory buffer and to memory located on this memory buffer. As you can see, that can become a bottleneck pretty soon, where the connection to the host becomes the bottleneck. In this flow, in this more efficient, optimized flow, D1 can do peer-to-peer requests directly to D6 attached coherent memory. And the way D6 maintains coherence with the rest of the system is through a new flow that got introduced in CXL3.0, which is called back invalidate. A back invalidate is a brand new flow that got introduced in CXL.mim. And the back invalidate flow essentially is a way for the CXL device to resolve any coherency conflicts that might arise as a result of peer-to-peer requests coming into this cache coherent memory by sending requests up to the host for, as the name suggests, backward invalidations. So the next thing I want to talk about is the concept of coherent memory sharing. So remember when we talked a little bit about memory pooling, one of the assertions that I made was in memory pooling, a single slice of memory can at most be assigned to one host at any given time, and not more than one. With memory sharing is fundamentally different because memory sharing allows for a CXL attached memory region to be allocated to more than one host at the same time. So in this particular picture, you have device D1, and D1 has a shared memory region called S1. And this S1 memory region, in this particular example, has been assigned to both H1 as well as H2. So both H1 and H2 can now access the shared memory region and have shared coherent copies of lines within this memory region cached in the CPU caches. The cache coherency for S1 will be maintained by the CXL device itself. So things like snoop filters, in-memory snoop filters, directories, etc., would be maintained by the device. And CXL 3.0 provides the semantics for the CXL device to be able to send snoops to H1 and H2 to maintain hardware coherency. Now, when you have a device that supports shared memory region, and we already had the concept of devices that maintain which did memory pooling. Now you can combine those two concepts together to create devices that have regions of memory that are shared as well as regions of memory that are pooled. So in this picture, for example, you have, let's say, a device D1. Let's say a majority of memory attached to D1 is a pooled device, and in this particular case, this memory has been allocated only to H1. However, there is a small sliver of memory in device D1 called S2 that is shared, and that is shared across H1 and in this particular example, H3. And similarly, you can have a multitude of such devices where you can now create configurable regions where the regions can be set up to be either shared or pooled. Okay. All of the orchestration of memory regions and who gets what memory in terms of either the memory is shared or pooled and how they're allocated to the host is done by an entity called the CXL Fabric Manager. The CXL Fabric Manager is essentially a controlling entity, and the interface between the CXL Fabric Manager and the devices or the switch is through a set of APIs that has been formally defined in the CXL specification. The last thing I want to talk about in this overview is the concept of fabrics. So for the very first time, CXL 3.0 defines a fabric. What is a fabric? A fabric is a system construction topology that is not limited by a tree structure, essentially. as you know, in traditional PCIe system topologies, as well as regular CXL topologies, they're based upon a tree structure where the CPU or the host is the root of the tree, and then devices and switches and intermediate elements are the branches and the leaves of the tree. On the other hand, a fabric system construction topologies allows for individual nodes to be connected to a set of intermediary elements that serve as a glue element for the fabric. What do we mean by nodes? The nodes can be any combination of CPU hosts, CXL devices such as Type 1, Type 2, or Type 3 device, or it can be a PCI device. What is the glue that forms the fabric? The glue that forms the fabric is a set of CXL switches. The reason we call this a fabric is because the glue allows for any-to-any communication between any nodes on this fabric in a peer-to-peer manner, but there is not a defined hierarchy or established tree structure, unlike traditional PCIe and unlike traditional CXL. This concept of a fabric is a very powerful tool in our arsenal because now it allows us to create system topologies and address use cases that could not be addressed using a traditional tree structure PCI topology. One example of one of the new concepts that CXL 3.0 introduces is that of a global fabric attached memory device. Now, a global fabric attached memory device is a piece of memory that is attached to CXL that can be accessed by any CPU that is connected to it either directly or through a CXL switch. And it differs fundamentally from the traditional processor-centric architecture by disaggregating the memory unit and putting it away from the processing unit. Now, in the past, we have had CXL attached memory that we refer to a Type 3 device. So what's different about a global fabric attached memory device or a GFAM device? The difference really is the fact that a GFAM device is defined generically to be an entity that can be accessed either in a tree-like topology or a traditional hierarchical topology like the one we know, or it can be part of a fabric and understands fabric semantics. And this creates a whole new set of opportunities for different usage models that can be addressed using a GFAM device, as we're going to see in subsequent slides. So one example of how a GFAM device can be used in the fabric context is that for a machine learning accelerator, as shown in this picture. So in this picture, what you see are a number of accelerators attached to individual hosts that are color-coded, right? And these accelerators and their host are connected all through a CXL switch and CXL fabric to a set of GFAM devices or global fabric attached memory devices. Now, what the fabric manager can do is that can create associations of these GFAM devices or memory devices to different accelerators. And thus, now what we have is a fungible resource for these accelerators to use for storing or for getting access to memory other than onboard memory. As you know, machine learning accelerators are highly limited in terms of their memory throughput and capacity. And really what they would like to have is a capability of expanded memory to fit in a larger working set and essentially work on a training model that may or may not fit on their onboard memory. The GFAM device gives them access to that resource. And as the slide mentions over here, the GFAM device is independent of the type of media that can be attached to GFAM, right? It can be DRAM, it can be non-volatile memory, it could be any emerging memory media, etc. Another example of fabric use case along with GFAM is shown over here, which is in, let's say, HPC or analytics. And in this system topology, what you see are individual hosts with their independent accelerators. And now instead of the accelerators being connected to the CXL fabric, it's the host that is connected to the CXL fabric. And this is particularly interesting and useful in HPC type systems where you have network cards that are communicating to multiple hosts, as well as network cards that are communicating to memory resources that are associated with these hosts. So, for example, on the right-hand side, on the bottom, you have a set of NICs, network interface cards, and you have a set of GFAM devices and these hosts that are all connected to this one fabric. Now, in HPC analytics, one of the common use cases are RDMA traffic, as well as messages, MPIs that are going over the network for messaging and communication, as well as traffic coming from the network that is depositing messages and data to memory. Now, when you create a fabric topology, you have a fungible, allocatable network through which you can configure what resources are allocated to which hosts and how the traffic and how data gets deposited to different memory resources on this fabric. And finally, we come to one last use case of CXL fabrics, which is to create composable systems with a spine leaf architecture. What's a spine leaf architecture? It's really a version of rack scale architecture where different sleds within a rack are optimized and specialized in different functions. So for example, in this picture, on the right-hand side, you could build a rack with different enclosures or different sleds. A sled might comprise of a network sled, another sled might be a CPU sled, another sled might be accelerator, and a fourth one may be of, say, a memory sled. Now, these sleds represent the leaves in this architecture. And these leaves are connected using a spine. The spine is really the CXL fabric. And as you can see, this is a way of building a rack scale architecture, which represents a peer relationship between the various sleds, which then allows us to create an all-to-all connectivity, which is extremely useful in terms of the degrees of freedom it gives us for efficient data and pointer movement between the network sled, the CPU sled, accelerators, and memory. And with that, we come to the summary. With CXL 3.0, we have doubled the bandwidth, introduced zero latency, and with doubling the bandwidth and with zero latency, we have a bunch of new features that we introduced. Those features include enhanced memory pooling, memory sharing models that we saw. We saw new features with multi-level switching, new fabric capabilities, and fabric management capabilities. We talked a little bit about the new symmetric coherency flows with backward invalidation and unordered I/O flows, as well as the improvement in software capabilities with the standardization of the CXL Fabric Manager. All of these features that we introduced with 3.0 are really addressing new usage models that are being brought into the consortium through CXL member companies. These usage models center really around the need for higher bandwidth as well as optimized system flows. It's not sufficient now to just double the bandwidth and not address the fundamental limitations to how that bandwidth can be consumed. And CXL 3.0 is fundamentally about doing both. Our call to action is to join the CXL consortium and follow us on social media for further updates. With that, thank you very much for listening to my presentation. Bye.
Thank you, Ishwar, for kicking us off. Virtual round of applause. I'm just going to clap for Ishwar. Do we have Ishwar on the video? Yeah, let's move on to the next session and then we'll come back to Ishwar. Sorry about that. So our next session is a coherency deep dive, and that's led by Rob Blankenship. Rob is a senior principal engineer at Intel Corporation, and he is part of the IO technology and the standards group. His expertise is in cache coherency protocols and memory interfaces for server products. Rob is one of the key contributors in the CXL consortium since its founding in 2019, and is currently the co-chair of the CXL protocol working group. let's go with the next session.
Hi, I'm Rob Blankenship. I'm from Intel Corporation, and I'm here representing the CXL Consortium as the Protocol Workgroup Co-Chair. I'm going to be doing a coherence protocol deep dive for CXL. So for my agenda today, we'll be going over kind of a primer on coherence and caching in general. Then we're going to get into a deep dive on the CXL.cache protocol, CXL.mem protocol, and focusing on some of the new enhancements we've added in CXL3, and also some of the new use cases that come along with those enhancements in the protocol. Okay, let's jump into it with the caching primer. So caching, what it does is it brings data closer to the consumer. So I have an example on the right over here where we have an accelerator that's accessing host memory. If it's accessing host memory directly, it's going to take about 200 nanoseconds, and that host memory is going to have a shared bandwidth of about, let's say, 100 gigabytes per second in my example. Now, if that accelerator can instead bring that data into its local data cache, now it can reduce the access latency to about 10 nanoseconds, and it will have dedicated bandwidth that's much higher, about 100 gigabytes per second, just for the accelerator. So how do we bring that data into the cache to get that better performance? We'll talk about two mechanisms normally in computer architecture. One is prefetching, and the other is locality. Now, prefetching, as it sounds like, we bring the data into the cache before it's required. That could be done either with hardware or software algorithms for predicting the data that's going to be consumed in the future. Locality is basically saying, hey, when I access an address X, it's likely I'm going to be accessing address X plus N in the near future for a given algorithm. So if I bring in the data into the cache in, let's say, a 64-byte chunk, and I'm accessing 4 bytes at address X, as long as X plus N is within that 64-byte chunk, it's going to be there when I go to access it, so I won't have to go back to host memory. Temporal locality says something similar, except that I'm accessing the same data multiple times. So repeated access patterns, this is called temporal locality. We're accessing the same data over and over, and if we keep it in the cache, we avoid having to go to host memory every time. So looking at a modern CPU cache hierarchy, how does CXL caching fit into that hierarchy? So showing an example on the left here. Now, most modern CPUs have multiple levels of caches. We have an L1 cache that may have the smaller capacity, but does have the lowest latency and highest bandwidth per source. Higher level caches have less bandwidth, but likely have much, or should say less bandwidth per source, but have much higher capacity and support multiple sources. Now, in the CXL context, you can see we have CPUs in this case, which have their cache hierarchy. A CXL device, as shown on the bottom in this picture, may also have a cache, which in this case I'm showing caches of around 1 megabyte for each device. And these sit as peers to the CPU cache within the cache hierarchy. Now, the cache hierarchy where CXL sits is as a peer to the CPU, and you can see within the modern, within a CPU, it's likely that they would have their own coherence protocol to connect between CPU sockets or between devices within the CPU socket. And it also has its own proprietary protocol for communicating to the home agent. And now we can see behind the home agent, or on top of it in this picture, we have native DDR, but we also have CXL-MEM. And we'll talk about CXL-MEM in a later part of this presentation, but it sits at a different location within the memory and cache hierarchy than where the CXL.cache protocol sits. Now, talking about cache consistency, right? When someone updates a location in memory, how do we make sure that data is visible to the other agents? Well, the basic mechanism is to say before you update a location in memory, you need to invalidate all the peer caches that might have a copy before you do the update. Now, this invalidation and cleaning up of pure caches can be managed with software in some cases, or with hardware. And software can add a lot of overhead. With hardware, we hide that overhead and manage it all in hardware. And this is what the CXL coherence protocol does. Well, for cache consistency, we need to define a point of global observation. So the source that's creating data knows when its new data is visible. And we'll talk about that within the flows coming up later. The tracking granularity for coherence is called a cache line. And in CXL, this is 64 bytes. All addresses for accessing memory in CXL are assumed in the CXL cache protocol are assumed to be host physical address. This is true both in the cache and the memory protocols. We support translation services done through address ATS. ATS is defined by the PCI Express spec. We use that same mechanism in CXL. So the cache coherence protocol we use in CXL is the same as base protocol used in most modern CPUs. It's called MESI or MESI. Those are the protocol states. So M represents modified state, where the data is only in one cache, can be read or written out of that cache, and that data is not up to date with respect to memory. That's modified indication. Exclusive is an indication similar to modified, where it's only in one cache, can be read or written by the source, the owner of that cache, but the data is up to date in memory. So it's different in that it is up to date. Now, shared state is a state where it can be in many caches at the same time, but the data can only be read, and the data is also up to date with respect to what's in memory. And invalid is, as it said, is the data is not in your local cache. Now, MESI states are tracked for each cache line. Cache line address in CXL is 51 down to 6. We have 52 physical address bits, and the lower address bits, these bits are aligned to 64-byte cache line, so the lower address bits are unused in the context of cache coherence protocol. Each level of the CPU cache hierarchy needs to follow the MESI protocol, and the layers above must be consistent. I'm talking about this today mostly in the sense of a flat protocol, but there are additional levels of complexity as you build up layers of coherence protocol. Other extended states are possible on top of MESI, but the CXL protocol only covers the base MESI protocol. So how are pure caches managed? Pure caches are managed by the home agent within the level of the cache hierarchy. So the home is kind of the arbiter that figures out which caches within its hierarchy have a copy of the line and resolve contention based on that. A snoop is a term used when the home needs to check the cache state or change the cache state of one of the caches it's controlling. Examples of CXL snoops are snoop invalidate. This causes the cache to downgrade to I state and must return any modified data. Snoop current is an indication that the home does not want to change the cache state, but it does want to know if there's any modified data in a cache. So it needs to get a copy of any modified data to make sure it has the most recent version. Okay, next we're going to start doing the deep dive on the CXL.cache protocol. So the cache protocol has a simple set of 15 reads and writes from the device to host memory. We try to keep this complexity low for these access types where we have the host manage all the global coherence, and the device just has to know about what cache state it wants, how it wants to commit the data, and deal with some snoops. CXL3 now enables up to 16 cache devices below a root port, where prior generation we were limited to 1 for each root port. So this is a big expansion in terms of the scale that we can get with the cache protocol. Now the cache protocol requires 3 channels in each direction. We refer to those channels as D to H, or device to host, and H to D, host to device. In each direction we have data and response channels that are pre-allocated. The D to H request channel is from the device, is for the requests and reads and writes to memory. The H to D requests are snoops from the host, where they're changing the cache, asking for cache state changes in the device. We do have one ordering rule within the .cache protocol, and it's that the H to D requests, or snoops, must push prior H to D responses when they're to the same cache line address, going to the same device. But aside from that ordering rule, everything else is considered unordered. Now I'm going to talk about a flow diagram here. In this flow diagram, we represent in the X dimension the different agents involved. So we have a CXL device. It also shows its cache state at the beginning of time at the top. Same with a peer device, where its cache state in this example is E state at the beginning of time. We have the home agent and the memory controller. And then, as I was implying there, the Y dimension is time. So as messages flow down this graph, it's over increasing time. So let's jump into the read example, where we have the CXL device is issuing a read to the home. It's a read shared, asking for shared state. The home is now going to snoop the peer cache because it knows the peer cache has a copy of the line, and that snoop data is going to cause the peer cache to go from E to S, and the peer cache will send a response. Now, once the response is received at the home knows that the coherence has been resolved, and it can give this S state to the device. So it sends this message that we call GOS, global observation for S. And then the home also sends the data after it's finished getting the data. In this case, it got the data from the memory controller, and it forwards that to the device. Now, mapping that flow back to the cache hierarchy we looked at earlier, we do have the device itself is at the bottom, connected on the CXL port, sitting within the cache hierarchy of the CPU. Peer caches could be, in that flow, could be a peer CXL device, it could be a peer CPU cache, it could be a peer CPU socket, and caches within that socket. It could be the right ordering queue or right ordering cache that we use for translating ordered PCIe traffic into the coherent domain. So it could be any of those. The flows look the same. Now, whereas the home agent, the final home agent, could be in the local socket where it's representing memory. That could be DDR or CXL mem, which is the protocol we'll talk about later. Could be in a pure CPU socket that the final home is for a given host physical address, either location. All right, so next let's talk about a write flow. This is example number 2. Traditional write in a cache will consist of 3 states. First, or 3 phases. First phase is ownership phase. Second phase is where we actually do the update of the data within the cache. This, I'm referring to that as a silent write. And then later there'll be a cache eviction where we flush the dirty data, modified data out of the cache. So the ownership phase is basically a read, just like the other read we looked at, except in this case we're doing a read own, meaning we want to get ownership of the line. So just like the other read, we snoop. Once we collect snoop responses, we get the go, in this case, E indication, and then data sent. Now, once we have E state in the cache, we can write it whenever the data is ready to be written. And that is indicated as a transition from E to M state. And then at some point in the future, that M state may get written multiple times from the device, may get read, but when the device is done with that data, it's going to do the cache eviction. And that looks like this flow, where we have dirty evict is sent from the CXL cache device towards the host. The host, when it has resources to sync the data, will send the go write pull, and then the data will be sent to the home, where in this example we're flushing the data to memory. It could also be written into an LLC or a cache level within the host cache hierarchy. Now, another type of write we have is what we refer to as a streaming write. In this case, the device doesn't have to get ownership first. It just issues the write towards the host, and the host will resolve all the coherence, as shown in this picture where we're snooping. Once we've resolved coherence, we'll send the go write pull, and then the data will be sent to the host. This is more efficient in that it has less messages on the CXL interface, but there is a downside. The downside is that when you send one of these writes, you won't know that the data is visible to peers until you get the go write pull message. So if you have ordered write requirements, so if you're writing address A and then later you need to write address B, and we can't write address B until we know A is observed, then this may be a bad flow, because that ordered traffic, that A-B ordering, means that we can't start the write to B until this write gets the go write pull, which means bandwidth would be reduced. So if you have ordered traffic, writing within the cache is going to be much more performant. Or if you're going to be reusing data multiple times, writing within the cache is more performant. But if you have unordered write transactions, this type of flow is going to be the most efficient to use from the device towards the host. And again, the host may install the data in the LLC instead of writing to memory, but in this example, I'm showing writing to memory. All right, so just to summarize the requests that we have in the CXL cache protocol, we have 4 read types shown here. We have something we call a read 0 request type. This is a read where we're getting no data, 0 data, but we are getting cache state. So we're doing a read on with no data. We have a cache flush. These messages don't return data, but they do impact cache state. Then we have 3 write types: dirty evict, clean evict, and clean evict no data. These are when we're evicting data out of the cache, either in a dirty or a clean state. And then we have the streaming writes, and there are 4 different flavors of streaming writes with slightly different semantics, but the basic flow is the same, where we're writing data to memory without getting cache state. Okay, next we're switching into the CXL memory protocol. So the memory protocol is really simple reads and writes from the host to memory. This protocol is technology independent in that the reads and writes doesn't matter if it's HBM, DDR, or persistent memory. The commands all look exactly the same. We do have architected hooks to manage the persistence of memory for memory that is persistent through power failure. But aside from that, the protocol itself is technology independent. The protocol does include 2 bits of metastate per cache line. This is an optional feature for memory devices. For memory-only devices, it's up to the host to define the usage of these 2 bits. Now for accelerators, the host encodes the cache state that the host is requesting in those 2 bits. And this is for cases where the memory is coherent between the host and accelerator. And in terms of the host managed device memory that we expose in the protocol, it comes in 3 types. First, like I mentioned, we have host only coherence, the HDMH. We have device managed coherence, HDMD. And then in CXL3, we've added some extensions on top of HDMD. We call that device managed coherence with back invalidate. That's the HDMDB feature that's new in CXL 3.0. So we have 3 channels in each direction for the memory protocol as well. And in the memory protocol, we refer to the M to S direction, or the master to subordinate direction, for sending requests from the host side, master side, to the subordinate. These are either the request channel or request with data channel. The S to M direction is the device sending either non-data response or data response back towards the host. These channels are pre-allocated. Those should have guaranteed resources to sync. And then we have two additional channels which are new in CXL3. We have M to S BI response and S to M BI snoop. This is used for the HDM DB memory type I talked about, where the device is managing coherence with the host. And I'll talk about those in detail coming up, but this is basically allows the device to directly send snooping type messages towards the host to cause the host to change its cache state, similar to what we saw in the .cache protocol. Now the .mem protocol has some limited ordering rules. One is the request channel, specifically in the HDMD memory type, which is for CXL2 and prior accelerators. We expect the request channel to be ordered for same address. And then in the HDMDB memory type, we have the NDR channel is ordered for messages with the same tag, and this is to help manage conflict flows and make sure that we have consistent view of the cache state between the device and the host. Okay, in this example, I'm showing a write on the CXL mem protocol from the host going to the CXL memory device. This CXL memory device is the simple memory device that has the HDMH memory. It's providing 2 bits of host-defined meta value. This support for that meta value is optional in the device, but I'm going to show a case where it is supporting that value, storing that value. So in this case, the mem write is sent from the host. It includes meta field with the MC indicating that the meta value is valid, the valid encoding of 3 in the 2 bits. The red arrows are showing an example of how a device may write data to its internal media. It issues the write to the media. It's going to have the necessary ECC to meet the RAS requirements of that memory media. And it's also going to write the meta value of 3 that was sent. And that may be stored with the cache line, co-located with the media, or it could be somewhere else. That's up to the device to decide. Now, what the device needs to send a completion for the write, it needs to do that as soon as that data is visible to future reads. And that would likely be before the write's actually committed to the media. All right, so second example is a memory read. Again, showing a case where the memory read is including a meta value. Now, when a read includes a meta value, that indicates to the device that the device needs to read the cache line of data, but it also needs to update the value to the new meta value indicated from the host. So again, showing an example in red of how flow may work within the device. It issues a read to its media, it gets the data ECC back and the meta state. It returns that data and the old meta value to the host. And because the host provided a new meta value that's different from the value that's in the media right at this when the read occurred, it needs to then issue a write back again to the media with the new meta value. And that would happen in the background and would get completion. And that new meta value, after you send the data back to the host, the device needs to guarantee that that new meta value is visible to any future reads. Now the host can also send a read where it tells the device it doesn't want to update the meta value. So it sends mem read, meta field is equal to no op. So the device is just going to read the media, data is going to return, it has meta state of 2, it's going to return that meta state back to the host. But because it was originally encoded as no op, it knows that no updates required. CXL mem also includes the ability to do meta value updates without reading the data. So we refer to this command as a mem inval, where we're indicating a meta value, a new meta value. So just like the original read, the device has to read the media to get the meta value. That gets returned, and what gets returned to the device is a completion message without any data and the meta value that was stored in memory. And because a new meta value was provided, we're going to have to do the write to the memory media to update with the new meta value. Okay, now switching to the HDMD, HDMDB memory types. Initially, we'll go through a few of the common attributes of these two memory types. In both cases, the D represents device coherence, meaning this memory has the ability to be cached either in the host or in the device. Now, when we encode these requests, we include the meta value field, which is indicating the host cache state. In HDMH, this is kind of host specific, but in HDMD memory types, it's specifically encoded to indicate the state that the final cache state that the host will be in after the request is done, where A would indicate it's really modified or exclusive in the host. Shared would indicate, hey, the host wants a shared copy. Invalid would say the host isn't looking to cache this data at all. And if it's reading the data and it says invalid, it just wants a current snapshot. It doesn't want to put the data in its cache. Now we also include a snoop type field, which tells the device how to change its own internal cache state. So the host may request invalid state, but may also have a snoop type telling the device cache to invalidate its cache as well. So snoop invalid would say, hey, the device cache should be invalid at the end of this flow. Snoop data would say the device cache needs to be in shared or invalid state at the end of this flow. We'll show examples in the next few slides coming up. We also use this term device coherence engine, or DCO. This is the final arbiter of conflicts between host and device accesses. It's kind of managing the different cache state transitions, and it'll show up in the flow diagram, so we'll be looking at it in the next few slides. Okay, looking at the specifics of the HDMD memory type. So for HDMD, the host will access device using the CXL protocol, just like HDMH, and it indicates the coherence required from the host. Now, the unique part is that the device will use the CXL cache protocol to cause state change in the host cache. So if the device wants to cache its own memory and the host may have a copy, it uses the CXL cache protocol to tell the host to change its cache state. And this is unique in that the host has to detect the address as being owned by the device and trigger a special flow which returns a forward message. Now, because it's using a .cache protocol, these same channels can also be used to access host memory. This drives the requirement that the state in the device for tracking coherence in the host effectively has to be a full directory, something we also refer to as a bias table. So device needs state for every cache line that is exposed to the host memory. So a little more detail on that. The full directory or bias table basically says that device has state that's 1 or 2 bits per cache line, indicating if the host has a cache copy. And we use this term device bias to indicate that the state indicates the host has no copy. And this allows the device to directly access its own memory without going through the host. Now, the alternate state is that it's in host bias, meaning the host does have a cache copy. So a read would have to be sent through the host in the .cache channel to resolve coherence before the device could access its own memory. Now, optionally, this host bias state can track shared versus any state. And with the shared state, it basically allows the device, even if the host has a shared copy, the device may directly read its own data, but it can't modify that data without changing the cache state in the host to get exclusive. But it can do direct access for shared state. Now, it is a responsibility of the host to track any peer caches that may have a copy of the line when it's in this host bias state. So the device that owns the memory, all it knows is the host has a copy, or some cache behind the host has a copy. The host abstracts all the peer caches like we showed in the cache hierarchy picture earlier. Okay, so let's look at a flow, kind of showing the different pieces I described earlier. So we're going to do a read where the bias state is host bias. So you'll notice this dashed line is the boundary of the device. So the device cache has a couple different elements within it. It has the device cache itself, the decode, the arbiter of coherence, and device memory. So in this case, the device cache starts in I. It sends the read-on for address X to the decode. The decode looks up the bias table, finds that it's in host bias, so it sends that read-on the external CXL interface towards the host. The host gets this read to X. It resolves coherence by snooping the peers, and in this case, it decoded this read, this address X as being owned by the device that sent the request. So it does a special flow where it sends this mem read forward command on the CXL mem request channel to basically tell the device, hey, I resolved coherence for address X, go ahead and read it from your local memory. Once the decode receives this mem read forward X, it can send the go message to the device cache indicating it does have exclusive state. It can send the mem read forward onto the memory controller within the device, which will read the data and return the data to the device. And at the end of this flow, the bias state is in device bias because the host cleaned up its cache state, no longer has a copy based on the request type that was sent. The device knows that the host is now in I state, so it can move to device bias. Okay, now showing the alternative flow, which starts out the same, where the device cache sends the read-on for address X to the decode. But in this case, it finds the bias state is in device bias. So it doesn't need to send anything on the external interface to the host. It can immediately give GoE to the device cache. It sends the mem read forward directly to the memory controller, which returns the data and the message. The request is done. Data is installed in the cache, and no messages showed up on the external CXL interface. It was all confined within the device. Okay, now we're going to look at the flow for the device cache evictions. So when the device cache is going to evict data to its own memory, it started out in M state, and it issues a dirty evict to the address X to the decode. Now, because it was unmodified, we actually knew that the data must be in device bias. So it's required when the device cache is exclusive or modified that the bias be in device bias. So we never need to inform the host when we're writing its own internal memory. So we can send the go write pull directly. The data is then returned to the decode, which sends the mem write to the internal memory controller and completes the transaction. Now looking at an alternative way to write, this is where we're not writing data within the cache, but we're doing the streaming write type flows. So device cache wants to issue a streaming write, issues a weakly ordered write to address X. Again, we find the bias state in host bias in this case, so we forward that weakly ordered write onto the host. Host does the snooping, and again, it detects this address X as being an address that is owned by the device itself. So it will send, in this case, the mem write forward for address X back to the device, indicating to the device that, hey, you now have exclusive ownership and are able to write the line directly. So we send the go write pull device cache. It sends the data, which is then forwarded to the device, its internal memory controller, and it's completed back to the decode, and then external complete indicates to the device cache that this data was in fact committed to the memory controller. Now at the end of this flow, we've also changed the bias state to device bias because we know that the host is in invalid state after we get the mem write forward. So the final resolution is device bias and memory is updated. And the alternative, similar to the read, is that the weakly ordered write may find that the bias is in device bias, in which case it doesn't need to go on the CXL interface at all. it would just send the go write pull data, reflects that data to the device memory controller, and completes and gets the external complete without ever going on the external interface. Okay, so now I'm going to get into the details of the HDM-DB memory type. This is the new enhancements in CXL3.0. So HDM-DB is device coherent memory with the back and validate channels. So back and validate channels are the BI snoop and BI response channels that were added in CXL3 to optimize coherence management. This enables the use of inclusive snoop filters, no longer relies on the CXL.cache request channel like we showed in the HDMD case. Now we do use the same bias table states for tracking coherence in the host, the I, S, and A states. The inclusive snoop filter architecture may block the CXL.mem request channel waiting for the back and validate snoops to complete. So when the inclusive snoop filter has capacity eviction, it may need to be sending this BI snoop to the host, telling it to change the cache state of prior cached lines, while it's doing that, it may need to stop accepting new requests, waiting for the capacity of that snoop filter to free up to enable processing of the new requests that once cache state in the host. And by creating this new allowance, we basically allow the inclusive snoop filter to be sized for the expected caching in the host instead of being sized for the entire memory capacity like the full directory would do. It should be a more efficient architecture for most implementations. Now, talking about the flow in particular and where the inclusive snoop filter comes into play. So let's look at the flow here where we get the memory to address X is sent from the host towards the device, and it has the normal meta value and snoop encodings. Now the deco within the device gets this request, but in order to process it, he needs to do a snoop filter eviction. So the snoop filter misses address X, but snoop filter, in order to process this address X, it needs to victimize address Y. So it's going to send a BI snoop to address Y towards the host. Now the host is going to get this BI snoop inval to Y. It's going to snoop its peer caches that we can see they started out for address Y, started out in M state. So the snoop occurs to that peer cache. The host home agent logic is going to, send the snoop, get the snoop response and the data. This is dirty data, so it needs to do a write back, a mem write for address Y towards the host, updating the dirty data in the host or in the device's memory. Once that write for Y is committed, we get the completion, and you can see the media update to Y is occurring in the background. But once that write is completed from the host point of view, we'll send the BI response message indicating that the back and validate snoop inval to Y is actually completed and the host is in I state. And now the deco has snoop filter resources to process address X. So it allocates the snoop filter for X, and it had prefetched the read to X to its media in the background, so that data is ready. So it can then indicate to the host, hey, comp E is, you have exclusive state for address X, and you're getting the data for address X, and the memory is then completed. Now, back and validate snoop also allows us to do block accesses. Now, when I talk about a block, I'm talking about multiple cache lines that can be, where the state can be changed with a single command. This idea allows improved efficiency when we're sending BI snoop messages that cover more than one cache line. So we support either two cache lines or 4 cache lines with these block commands. Encoding is indicated in the message. So I'll show an example here where the device is doing a snoop filter eviction for a block of lines. So it has 4 cache lines, starting with address Y. but it's 256 bytes. So 4 cache lines that want to be snooped out of the host. So it sends this bi snoop inval block command for address Y. The host gets that command, and now it needs to go and validate all 4 cache lines within the host. It finds that only 2 are currently cached. So Y0, Y2 in this example. So it sends 2 internal snoops to clean up those 2 cache lines. Once the snoop responses are received back at the host home agent, the host home agent can now send a block response back to the device, indicating that all 4 cache lines are now invalid. And at which point, the device that had read this line, wanted the block read earlier, can now read the device media to get the 4 cache lines into the device cache, and also can give go for each of the 4 cache lines to the device cache. So the goal of this flow overall is to save the number of messages that show up on CXL and improve efficiency for this type of flow. So with HDMDB, we enable some new usage models. They'll be discussed in the next few slides. Okay, now CXL enables direct peer-to-peer with the HDMDB memory type. Now, when I say direct peer-to-peer, I'm talking about a CXL peer or PCIe peer writing directly to the CXL memory region that's HDMDB. Now, these devices, sitting below the same root port hierarchy can be decoded to go directly to the HDMDB region. The device with HDMDB can get those reads and writes using the CXL.io or PCI Express protocol and resolve coherence with the host using the flows we talked about earlier. Now, this is an advantage over HDMD and the HDMH model, where this accelerator must go through the host, and the host resolves coherence with the device. And in that model, we would load this link going from the switch to the host with this traffic. It would go up to the host and then back down on .mem. By doing direct, we reduce loading on that link, and we also reduce latency by giving a direct path. Now, pooled memory and shared memory in CXL existed in 2.0, this memory was in 2.0 assigned directly to each host. Now, in 3.0, we introduced this idea of shared memory across multiple hosts, and we also introduced the ability to keep that memory hardware cache coherent between multiple hosts. So we do enable both the hardware coherent model, where this memory might be mapped to 2 or more of the hosts, and the hardware cache coherence will resolve coherence using the HDMDB memory type, with the BI snoop channels resolving coherence between the different hosts that are accessing that region. We can also enable a software coherence model, where instead of having the tracking and the back and validate channels, software ensures that only one host, that the memory is consistent between the different hosts, so we don't require the tracking and the back and validate channel. And this may be useful for workloads where software knows and understands the handoff between the different hosts. This concept of multi-host coherence and fabric attached memory will be discussed more in the fabric tutorial. Okay, just to sum it up, we've looked through the protocols that we have in CXL, the cache and the mem protocols. These protocols have been evolving over time, and in CXL2 we added switching and the pooled memory capabilities to the protocols, and in CXL3 we've added the .cache scaling improvements to allow multiple .cache devices below a root port. We've added the back and validate channel to enable snoop filter, direct peer-to-peer, multi-host coherence. It's a powerful feature that's new in 3.0. And then we've also added the port-based routing messages. This will be covered in the fabric tutorial coming up next. Okay, I wanted to thank all of you for coming to the tutorial and listening today. do want to plug our website, computeexpresslink.org. You can join, become a member if you're interested in participating. There's Twitter, LinkedIn account, and then we have CXL Consortium YouTube channel where you can see more trainings and more information on CXL. Now we'll go to the audience Q&A. Thanks a lot.
Hey, thank you, Rob, for that excellent presentation on CXL coherency deep dive. Let's see if we can get Rob back on for the Q&A. Rob, can you hear us?
Hey, Nathan, can you hear me?
All right. Yes. Thank you.
All right.
So
Awesome.
I think we're going
Figured it
to go to you first, and then hopefully we'll get Ishwar back on.
Okay.
Is Ishwar on as well? Yeah. So, sorry for all the technical difficulties this morning. I mean, it's an incredibly complex system out here, so please bear with us. It's only day 0, tutorial 1, so yeah, it's hopefully we'll work out all the kinks soon. Okay.
So I took a few notes, Nathan, on some of the questions that came up. Do you want me to?
Yeah, go ahead.
Through some?
Yeah, so let me just ask with the first question.
Okay.
There were a number of questions around addressing, Rob,
Yep.
from Christoph Nowak and Tom Gooding from IBM. And I think I'll just summarize it. What's the total size of the addressable space? And could that be a limitation for large-scale CXL systems with huge amount of NVM3 type devices?
Yeah, we currently are limited to 52 host physical address bits, which means 4 petabytes of memory. Now that is per host. So if you have multiple hosts, each host can have that much address space, and that can. So we do get with multiple hosts, you can get beyond that. But in the future, if we find that 52 bits is limiting, we could do enhancements or extensions to allow larger address space.
Okay, so we definitely are going to consider perhaps a little bit increasing the physical address space in the future, right? Perhaps in CXL4 or later.
Yeah, I think that's in scope for sure. But again, we'll have to see how capacity evolves over time.
Right. So there's also a number of questions around the cache line sizes. Jeff Smith from Citadel Securities asks, are different sized cache lines under consideration for future CXL generations?
Yeah, generally our coherence protocol on both the cache and mem side are built around 64-byte cache lines. A device or host could have internal mapping where I think Tony mentioned this in the responses too, where you could do 128-byte cache line and internally, but translate that to 64-byte management on the CXL interface. But so I think there are things devices or hosts could do to have different sizes, but generally protocol we've defined is assume 64-byte cache line. No current plans for changing that.
Thank you, Rob. There's another question from Mingyao Shen from UCSD. Since CXL 3.0 supports memory sharing, how is the coherency implemented for shared memory? Is it also done by CXL.cache and the backend validation of CXL.mem?
Yeah, generally, right, CXL.mem is the protocol where the host, it's for the address space that the device owns, that it's exposing to the host. For all other address space, if an accelerator wants to cache the memory, it uses the CXL.cache protocol. So the two protocols are isolated from each other in terms of a given device would use, it's either using addresses on CXL cache for memory that it doesn't own, or CXL mem for the addresses it owns. I don't know if did I hit the question?
I think you hit it.
Okay.
Another question from Nadine Guevara from Imperial College London.
Mhm.
Does device bias imply that coherency is not enforced across devices?
Well, again, the idea of bias is for the memory that the device owns. So when it is, coherency is maintained across all the cache hierarchy, including peer devices. So when the bias table says it's host bias, that could mean the host is caching it, or it could mean a peer device is caching it. From a device point of view that owns the memory, he doesn't know the difference. And that's part of the value of CXL is it hides some of that complexity from the device and lets the host manage where the peer caches are that may be caching the memory that the device is providing.
Thank you, Rob. Next question from Shinichi Shibahara from Renesas. What protocol is expected on coherent CPU to CPU symmetric links? Does CXL3 support CPU to CPU cache coherency?
Generally, CXL is defined and optimized for host connection to devices, following PCIe sort of topologies. The connection between CPUs, the symmetric link that I showed in the picture, that's really defined by the CPU vendor. CXL isn't trying to directly address that. We understand that it's there and make sure that we support different host CPU architectures, but we don't define the link between the CPUs, at least not in this generation. Our focus is really on host connections to devices.
Thank you, Rob. Please stay on. Can we get Ishwar on? Hey, Ishwar.
Hey, Nathan, can you hear me?
All right, let me find, yes, I can hear you.
Excellent.
Thank you. So let me go back to the first question that I asked. Is the CXL Fabric Manager typically software that runs on CXL switch? This is from Ronnie Krasinski from NVIDIA.
Yeah, so the CXL Fabric Manager, as defined by the CXL Consortium, is an orchestrating or controlling entity. It's really an abstract concept. The physical manifestation of this abstract concept can be software running on the host, some sort of firmware running on the CXL switch, or some firmware running on an external microcontroller that is connected on the board, just like perhaps like a BMC or things of that nature.
All right, so there's another question, and I'm going to generalize it a little bit. This is from Bob Wheeler from Wheeler's Network. So many standards like OpenCAPI and GenZ have been merged with CXL. How does CXL 3.0 leverage and use GenZ IP? And did GenZ accelerate particular aspects of 3.0?
Yeah, absolutely. So a number of standards are being kind of merged with CXL. These standards, such as OpenCAPI and GenZ, have donated their assets and their IP to the CXL Consortium in order to consolidate the industry behind the standard to accelerate our efforts. The CXL Consortium is continuing to investigate how to best leverage the assets and IPs from these consortiums for ongoing work on a case-by-case basis, including, for example, in CXL fabrics.
Thank you, Ishwar. There's another question from John Golenbisky. Is a GFAM basically a memory device that also has a tight affinity for a specific host that bypasses the CXL switch?
So yeah, a GFAM is a memory device model, right, which allows for a CXL attached memory to be allocated or affinitized to one or more hosts. And the device model allows for this device to be accessed either in a tree topology, like a traditional CXL network, or on a CXL fabric. So the question, so the way to think about GFAM is that it makes the CXL attached memory more generic in its definition and the way devices can be constructed such that the devices can be part of a traditional CXL attached switch or directly connected to the host, or the device could be part of a CXL fabric and then be connected to a wider network with a peer-to-peer relationship.
All right, final question for you. This is from Nadine Guevara.
Mm-hmm.
How can GPUs leverage CXL for machine learning?
Great. So GPUs actually can be thought about in two ways, in my opinion. One of them is you can think about a GPU with machine learning capabilities as a CXL Type 2 accelerator with device-attached memory that participates in coherency flows with the host using the backward invalidate flows or using bias-based coherency. So that's one, right? The other one is the GPU could be part of a CXL fabric, right, where it communicates with other peer GPUs, it communicates with a network interface card, and most importantly, it communicates with global fabric attached memory or GFAM, and is part of a scale-up network of GPU devices. So those are two potential models on how GPUs for machine learning can utilize CXL and make it more powerful.
Thank you, Ishwar. All right, if we can get Rob on, one final question. Hey, Rob, you're in the middle of this, so it's probably not an easy question, but let me ask you. Rahul Toli asks, where does security come into the whole CXL protocol philosophy? Is it CXL.io? Does that enable other CXL channels to establish communication channels?
Yeah, so in CXL 2.0, we added the link IDE extensions, which allow us to securely encrypt and and all the attestation requirements around setting up secure channel between host and device, host and switches. Now, the higher level, maybe higher level security issues around trust, being able to isolate between different VMs running in the host, that's kind of work still to be done that we can expect to see in the future. But we have some fundamental security attributes that we're going to be building upon that are already out there in 2.0 and 3.0 definition.
Thank you, Rob and Ishwar.
Mm-hmm. Thanks, Nathan.
Thanks.
Thank you very much. All right, we'll go to session 3. This session is being led by Prakash Chauhan from Meta and Mahesh Wagh from AMD. And this will focus on memory attach over CXL and the challenges being faced. They touch on a very broad range of topics, which includes RAS, error handling, telemetry, device types, pooling, software, and a lot more. Prakash Chauhan is a hardware technologist at Meta. He has over 25 years of experience in designing, architecting, and deploying high-volume compute systems with focus on key metrics like cost, reliability, security, and performance. Prakash has been an early member of the CXL Technical Steering Committee and has been involved in developing the CXL specifications to support new and innovative system architectures. Mahesh Wagh is a senior fellow at AMD, where he is leading the server systems architecture for EPYC products. His expertise spans I/O subsystem architecture, coherency, and multi-chip package interconnects, hardware-software interface, and IP development. He has made significant contribution to CXL and PCI SIG. He is a frequent speaker at the CXL events and PCI SIG Developers Conference. He is a proud recipient of the PCI SIG Lifetime Contributor Award. Let's move to the next session, please.
Hello, everyone. My name is Prakash Chauhan, and I am a system architect at Meta. In this session, Mahesh and I will deep dive into the memory-specific aspects of CXL. We'll discuss the motivation behind CXL attached memory, the way it can be used to augment the memory hierarchy on servers, and how we expect it to evolve over time, and the major challenges to deploying CXL memory. Let's first look at some of the trends with regards to server memory. The chart on the right shows how main memory costs have evolved over the last 2 decades. The cost per gigabit went down exponentially until about 2013 and has since flattened out due to process scaling challenges. On the flip side, the demand for both memory bandwidth and memory capacity have continued to grow. This is in order to support system performance as CPU core counts have grown and workloads like AI and ML have become dominant. The result of these trends is that system memory costs are now the largest portion of server TCO and are growing rapidly. Adding memory capacity and bandwidth also leads to some system design headaches. Current systems require adding more DDR channels to the CPU or moving to faster data transfer rates. However, because DDR is single-ended, each channel added adds a couple of hundred pins when we account for signals and power. This leads to expensive sockets and reduced reliability, as a good contact is needed to be maintained over many thousand of pins. We also need to add additional PCB layers to route these additional channels of memory, which increases PCB costs. Higher data rates also come at a cost. In order to maintain a reliable interface, we need to have better signal integrity, which means we need to minimize reflections and crosstalk. And crosstalk becomes really important for these wide parallel buses. To achieve high signal fidelity, we need to reduce pad capacitance and via stubs, which can lead to expensive manufacturing processes. To remove the effects of inter-symbol interference and reflections, signal processing elements such as DFEs are needed, which increases power and circuit cost. As data rates continue to ramp up, we might have to live with 1 DIMM per channel configs, which cause further problems with scaling the DRAM capacity. So how does CXL help with these challenges facing server memory? CXL is the first widely adopted standard that allows memory to be decoupled from the CPU. It is designed to allow the host CPU to perceive CXL memory exactly like CPU-attached memory, which means load store accesses and fully cacheable space. CXL is media agnostic, unlike the CPU-attached memory channels, which are usually cutting-edge DDR. CXL also mitigates system design issues by using differential signaling, which reduces CPU socket pin counts by over 2/3 and is naturally tolerant to crosstalk. As mentioned in the previous slide, CPU-attached memory can only be of a single type, DDR, which is optimized primarily for performance. In contrast, CXL allows adding Type 3 devices that allow system designers to build a memory hierarchy, which can allow for optimizations in the cost, capacity, and performance axes independently. Let's look at some of the system design benefits of CXL. With CXL, one can design a single base system that can be adapted to different applications. For example, on the left-hand side, we have a system that might work well for applications that don't scale up significantly with additional core counts or memory. On the right-hand side, the same base system can support higher memory bandwidth and/or capacity to enable applications that scale up well with more cores and memory. The CXL memory can also be tiered to allow lower cost or lower power, and by using software techniques to ensure that performance is not impacted while lowering the overall system TCO. Let's look at a concrete example of cost savings with CXL. Assume that we have a CPU with 80 cores and 8 DDR channels at 1 DIMM per channel. Further assume that the application needs 2 gigabytes per core in capacity. So we need a total of 160 gigabytes of memory capacity. However, using 16 gigabyte DIMMs, we can only get to 128 gigabytes. If we use 32 gigabyte DIMMs and populate all channels, we overshoot by almost 100 gigabytes, and at $5 per gigabyte, we would be paying nearly $500 more for unused memory. We could choose to populate only partial channels to get to the right capacity, but this leads to odd interleave sets and loss of aggregate bandwidth, which might be unacceptable for performance. Using 16 gigabyte native DIMMs and 32 gigabytes of CXL memory, we can get to the right capacity and also introduce additional bandwidth to the memory subsystem, which can lead to increased performance. Moreover, the 32 gigabytes of capacity could be a cheaper media type, further reducing costs. Now let's look a little bit at the evolution of CXL-enabled memory products. The first generation of CXL memory products will include memory modules that are directly attached to CPU root ports. They will likely be CXL 1.1 compliant with some CXL 2.0 features and will bring up the capabilities of adding memory capacity or memory bandwidth or support for lower cost media types in a system. The second generation of products will include full CXL 2.0 support and will allow memory pooling, which has the promise of reducing the overhead costs of CXL infrastructure, like the board and ASICs that are needed to attach memory. Additionally, this will also allow making flexible allocations on an as-needed basis to avoid static over-provisioning of memory on each host. The third generation of products will leverage capabilities introduced in CXL 3.0, such as coherent sharing of CXL attached memory. This will enable applications to scale up using shared memory communications and reduce memory footprints by keeping one copy of the working data set, as opposed to replicating it on all compute nodes. In the fourth generation, we will see products that will take full advantage of CXL 3.0 features, such as multiple levels of switching, to support large-scale disaggregation of memory from compute, as well as scaling up to the very large data sets across a large number of compute nodes. Now I will hand over to Mahesh to talk a little bit about AI-specific applications and tiered memory.
Thanks, Prakash, and hello everyone. My name is Mahesh Wagh, and I'm a system architect at AMD. Let's continue the discussion and take a look at an example of AI memory topology. AI ML HPC workload requires distributed computing over a large dataset. CXL 3.0 provides the infrastructure to enable scale-up and scale-out solutions. CXL 2.0 limited the number of accelerators that could be connected below a CXL hierarchy. With device scaling, CXL 3.0 opens the solutions to support multiple accelerators to be connected to the CXL hierarchy. CXL switching extends the support by enabling multiple levels of switching and adds the capability to share memory across nodes. This type of shared memory is referred to here as GFAM or Global Fabric Attached Memory. CXL 3.0 provides the ability to enable a path for direct peer-to-peer accesses between I/O networking devices is an example, and memory in the node or shared memory without having to bounce off those requests through hosts. The Fabric Manager is responsible for orchestrating and managing the resources shared in such a system. These enhancements enable compute to happen near the data, improve system efficiency, power, and cost. This enables CXL 3.0 to scale the solutions at the fabric level. Next, we will dig deeper into the tiered memory architecture, a fundamental enabler for several CXL memory expansion usage models. The concept of tiered memory isn't new in the industry. Tiered memory categorizes the memory access into different tiers based on performance, with the hot memory being associated with the highest performance, lowest latency, for example, with direct attached DDR, and cold memory associated with low performance, such as disk accesses to NVMe drives, and one or more tiers in between. Some examples of the use cases are mission critical applications are mapped into hot memory, large volume data accesses could be mapped into cold memory, and less frequently accessible information can be mapped in the in between tiers. One of the ways to identify these tiers is by mapping them into NUMA domains, non-uniform memory access domains. The concept of NUMA domains isn't new either. Many host processor architectures already support grouping their internal resources and memory regions into NUMA domains, thus providing performance optimization options for memory management software. NUMA domains can now cover CXL attached memory. What CXL is bringing to the industry is the concept of a zero-core NUMA node, a tiered memory region consisting of CXL memory expansion devices without any cores associated with it. Before we dig deeper into tiered memory support, it is important to understand some key enablers. First and foremost, it is going to be very critical for the ecosystem to establish that CXL attached memory is functional and performant. This will require the ecosystem to work together in optimizing and characterizing the CXL memory expansion solutions. For example, understanding the latency bandwidth characterization of a CXL memory device across unloaded and loaded latencies is critical for targeting certain applications and optimizing solutions. For example, to get a balanced performance, the memory manager would like to limit the operating bandwidth to the flat region of the latency bandwidth curve. Such information about latency bandwidth curves would also be useful to see the impact of tail latencies on bandwidth. While there is a lot of work cut out for optimizing performance, a typical recommendation for direct CXL attached memory is to be equal to or less than access to remote socket attached memory, for example, remote DDR. Several studies have been conducted using two-socket systems to simulate CXL attached memory and for the development of memory management proof of concept software and to characterize the impact of tiered memory, the zero NUMA on applications. CXL specification provides mechanism based on ACPI objects such as CDAT, SRAT, SLID, and HMAT to describe the latency and performance characteristics of the attached devices. This information can then be used by software to calculate the NUMA distances, proximity domains, and then used for memory allocation decision, runtime memory management policies. During runtime, we expect accesses to be made simultaneously to both the hot as well as warm tiers. If this is not carefully controlled, the access to a warm tier could end up consuming common resources and impact access to hot memory. Quality of service features that guarantee a balanced performance are critical for tiered memory solutions. These could be host access control mechanisms such as rate metering or mechanisms based on device feedback. We'll talk more on device load-based QoS telemetry in upcoming sections. We expect the industry to take a crawl, walk, and run approach with tiered memory. The desire is to keep the applications agnostic to tiering and deploy clever kernel or OS-based memory management and optimization techniques. An example of a simple memory management policy would be to allocate memory from the hot tier, and when you run out of the hot tier, then map memory from the warm tier. If the memory manager is aware of the application requirements, then some of the applications can be mapped to the tiers based on their performance requirements. Several schemes exist here, and several more are in development in this area of active memory access monitoring, allocation, and management. There is a technique of active page migration that is gaining a lot of traction here. Actively managing the page residence in hot or warm memory depending on access frequency. That's one example of such a scheme. Such a scheme can be broken down into three parts. Monitoring capability to identify the residency of frequently accessed pages, that is, which tiers are getting accessed and how frequently. A policy engine to determine which pages to swap between these tiers, for example, between the hot and warm memory, and then a mechanism to do the actual swap. There are several software development kits and development in the open source ecosystem for this dynamic tiered memory allocation and management. There are several companies building memory optimization layer services. I will now hand over to Prakash to give an example of one such development at Meta.
The next few slides describe some of the work done at Meta to take advantage of tiered memory. On the top left, we show a set of 4 large applications and their usage of memory. The red bars show the fraction of memory that is frequently accessed over a 2-minute period, while the blue bars show memory that is infrequently accessed. As can be seen, there is a large portion of system memory that is cold and is a good candidate to be moved over to CXL, which adds a small but significant latency as compared to native attached DDR. Other hyperscale companies have also published studies that show similar behavior where significant fractions of system memory are infrequently accessed or never accessed. Due to a huge diversity of applications in the data center, it is crucial that the first deployments of CXL memory should not require applications to change to take advantage of this memory. This means that a smart and application-transparent page placement technique is needed to place hot data in native memory and cold data in the CXL memory. Since CXL attached memory is exposed as a CPU-less NUMA node to the operating system, it might appear that existing NUMA-aware scheduling should be sufficient to provide good page placement out of the box. However, the existing NUMA support was not written for CPU-less NUMA nodes and leads to the following problems. Pages get allocated to local memory until there is no more space left, and the new pages overflow into CXL memory. This means that cold pages may be trapped in local DRAM that do not get migrated to CXL. And since there is no room in the local memory, a hot page cannot be promoted from CXL to local memory. This slide shows some design principles for transparent page placement, or TPP, developed at Meta. The main enhancements to the existing NUMA techniques are as follows. Firstly, we establish watermarks for native memory usage that trigger demotion to CXL memory when the native memory starts filling up. Secondly, we track pages on CXL memory as they become hot and promote them to native memory, while making sure that pages don't keep bouncing quickly between native and CXL memory. The TPP implementation has the following core tenets. It is transparent to applications, so page detection and movement are handled by the kernel. It's designed to converge quickly to reflect changes in application behavior and transient allocations such as request processing related memory and network buffers, etc. And it's reliable. It's been tested with real applications in a production environment. And it works globally, which is something that can be upstreamed to Linux and is not meta-specific. At this point, I'll hand it back to Mahesh to talk about some critical deployment-related challenges with CXL memory.
Thanks, Prakash. We will look into the deployment challenges, what has been addressed architecturally by CXL specification, and what are the areas where development is required, and the call to action. Let's start with RAS. The philosophy for RAS is keep it simple by mapping CXL attached memory related errors into existing error handling schemes where feasible. Some things are going to be new and require new mechanisms. We can categorize CXL error into 4 types. Poison. This is reported synchronously as the poison data traverses to the requester. This needs to be consistent with handling of poison data from direct attached DDR memory as an example. The handling of the error would be implementation specific. Implementations that take a machine check for poison data returned from direct attached DDR memory should also do the same, that is machine check for poison data returned from CXL attached memory. CXL attached DDR as an example. Viral. This also falls within the same category of handling. It is reported via CXL link. However, handling of the viral condition needs to be consistent with the fatal error handling for direct attached memory. CXL protocol errors. These are related to the CXL protocol and reported via PCI Express advanced error reporting structures. The specific internal error information is logged in CXL RAS capabilities. What is new here is that the PCIe root complex event collector collects the error information and signals that to the firmware or the OS for handling. The handling of the error is analogous to PCI root port handling. However, error handling software can now be enhanced to be CXL aware. Finally, it's the CXL component errors. These are errors that are detected on the CXL device and reported via CXL device component command interface using an architected CXL defined record format. There are two mechanisms that are supported here, firmware first or OS first. Firmware first uses vendor defined messages for the CXL device to signal component errors to firmware. The OS first mechanism uses MSI or MSIX to signal component errors to OS. This requires firmware and OS software development to handle component level errors. We'll take a somewhat closer look into the next level of details for CXL protocol errors and CXL component events. But before that, there is a call to action. While Poison and Viral can map into existing mechanisms, both CXL protocol errors and component events require new software development. Please help contribute towards software development of these critical RAS features. There are two paths that can be taken for CXL protocol error handling. The system administrator typically decides if the firmware first or OS first mechanism needs to be used. This is a very high-level overview of firmware first and OS first handling of errors. With firmware first, the platform firmware needs to follow an AER path to decode the errors. From there, the firmware then collects the CXL RAS capability information as part of the AER handling. The platform firmware will then use the CPER format that's used to represent data, and it will use the UEFI CPER format to collect that information. And finally, the platform firmware may signal to the OS through existing ACPI methods. On the OS first side of things, the OS must handle AER events through existing methods. The PCIe methods can now be extended to support CXL. If the AER status indicates that it's an internal error, it's either a correctable or an uncorrectable internal error, and then the source is determined to be a root complex event collector, then the OS must inspect all of the AER and CXL RAS structures of associated downstream ports. If the status indicates that it's an internal error and it's associated with an endpoint, then the OS must inspect the CXL RAS structure of the associated upstream port. Next, we'll talk about the CXL component event handling. The picture below shows the two paths that can be taken for the CXL errors, the firmware first signaling path or the OS first signaling path. In interest of time, we will discuss the OS first signaling path for component errors. We can divide the tasks into two categories, boot time tasks and runtime tasks. Let's first talk about boot time tasks. First, we need to ensure that OS gets control for memory error reporting. To do that, the operating system must request and be granted the memory error reporting control through _OSC. To query the device will require the software to access the component command interface. Now, this requires a CXL memory device driver to be loaded to manage and provide access. The operating system needs a CXL event service driver. It can leverage the CXL memory device driver to interact with the mailboxes, etc. This event driver will then implement and handle the polling timers and MSI/MSIX interrupt drivers for these events. Runtime tasks. Some examples of the runtime tasks for event driver are as follows. The event driver handlers will execute mailbox commands to get and clear records. We expect the event drivers will parse records and report to the user. The event driver may call other OS facilities to act on error information. So these are some of the examples of what the boot time tasks and runtime tasks are. So here's the call to action. This OS CXL driver development is required for enabling CXL RAS, and we expect the ecosystem to contribute towards this OS CXL driver development. Let's look into some of the challenges with QoS telemetry and what has been done by the specification to address that. We touched on the topic of quality of service during the tiered memory section. Access throttling, that is rate metering mechanisms as an example, are required when working with tiered memory solutions to ensure a balanced performance. This is to ensure that all of the resources do not get consumed servicing or accessing slower memory and impact access to the faster tier. Several host implementation mechanisms can be supported to ensure this balanced performance. These mechanisms can be further enhanced with an architected quality of service telemetry responses from the devices. Now, CXL 2.0 specification defines the QoS telemetry mechanisms that enable CXL devices to provide this timely device load notifications in their responses. These responses are architected to be immediate and ongoing, and when enabled, every response can convey device loading. This device loading information is encoded to inform if the device is lightly loaded, optimally loaded, or severely loaded. This information can then be used by the host to build throttling mechanisms based on device feedback. For example, back off when the device is reporting severely loaded conditions and increase the rate when the device load condition changes to optimal or lightly loaded. Device load conditions are then further categorized as internal loading, that is device conditions that are impacting servicing of the request, or egress port back pressure, conditions that are either system-wide that are causing back pressure on the egress port such that the responses are slowed down. Device can service requests, but congestion is perhaps somewhere in the system causing a back pressure on the port. And temporary throughput reduction, congestion or conditions at the device that are temporary in nature. Device load conditions are also architected to take care of devices that can support multiple quality of service classes. One example of this would be devices with different media types supported behind it, and as a result have different load conditions. Multiple quality of service classes allows for such a device to report its load condition per QoS class. Multiple QoS classes will require OS development to understand and map these multiple quality of service classes. Finally, multi-logical devices support sharing of resources across multiple nodes. CXL 2.0 specification has architected sophisticated mechanisms to handle QoS telemetry for this very special class of devices. This mechanism takes into account the access implications based on pooling resources. So here's the call to action on quality of service telemetry. Quality of service continues to be an important feature to guarantee balanced performance. Early implementations may build implementation-specific mechanisms and enhance them based on device support for QoS telemetry. We encourage the ecosystem to support this QoS telemetry support in their implementations. Lifecycle management of CXL devices is going to be important. CXL memory expansion devices are different than PCI devices because the CXL memory expansion devices extend the system memory. In general, there is no appetite for device-specific drivers as much as possible. To keep it simple, the goal is to extend the system memory capabilities for more capacity, bandwidth, and total cost of ownership optimizations. A CXL device will encounter several events that need to be managed. Firmware events, RAS events. If we take DDR as an example, what used to be a CPU responsibility for DIMM rank training is now a device responsibility, and there needs to be a mechanism to expose this to the system in familiar ways. Thermal events need to be monitored as well as device health needs to be monitored. To manage this at runtime requires a mechanism for notification of events, a mechanism to read the event logs, and a mechanism to issue commands to manage and repair devices. In addition to the device itself, there might be sub-FRUs like DIMMs, and proper identification of the failing DIMM for swap is needed as an example. You might have to read the device information for diagnostics or get the device capabilities information to configure the system optimally. These are just a few examples of runtime tasks. CXL supports component command interface to communicate with the device for these lifecycle events. These mechanisms can be supported through in-band or out-of-band mechanisms. So here's the call to action. Ecosystem software development is required for lifecycle management of CXL devices. There are many ways to go about doing it. The CXL event driver can be enhanced, or a lifecycle management driver can be developed. We would like the ecosystem to focus on building this very important capability. Security is critical for any system level solution. CXL 2.0 provides integrity and data encryption, an IDE solution for all traffic across all entities, that is, covering root complexes, switches, and devices. Link ID is link local and protects from interposer and replay type of attacks. Some of the early implementations will rely on implementation specific methods for security to service different threat models. There is significant work ongoing in the CXL consortium. There are proposals under development to meet the emerging security and confidential compute requirements. The call to action is contribute towards the development of security mechanisms, get involved with the consortium in the definition of this very important feature. Next, we will look into CXL memory device types and some examples of memory pooling. Let's first talk about a CXL single logical memory device. CXL 2.0 single logical memory device is a device that has one CXL link coming out of that device, and it can support one or more PCIe endpoint functions. A CXL 1.1 device will appear as a root complex integrated endpoint versus a CXL 2.0 onwards, the device will appear as PCIe endpoint. It's important to note that CXL device can implement more than one function. There is a function map DVSec that is used to advertise non-CXL functions, and that is used to identify which of the functions are CXL functions and which of these functions are non-CXL. The type 3 device component register defines the HDM decoders, and these decoders are used to map the host physical address. So this is the address that the CPU or the host will send down to this device. The HDM decoders also support the capability for interleaving, understanding which interleave offset the device belongs to, and that way it can do an effective mapping from host physical address to the device physical address. The CXL link in this example is connected to a single virtual hierarchy, which means this device and all of the memory allocated to this device is going to be mapped to a single host domain or is going to be mapped in a single address space. We'll then move to a multi-ported device as an example on the next slide. All right, so this is showing an example of a multi-ported device. What we mean by a multi-ported device is that it has multiple CXL links. So for example, it could have 4 CXL links as shown in this example, and each CXL link could be a by 4, a by 8, or a by 16, depending on how much amount of bandwidth through each CXL link the device wants to support. Behind each CXL link represents a single logical device that's connected behind that CXL port. And the definition for that single logical device is exactly the same as the SLD I was talking about in the previous slide. The key difference here is that this device is now capable of pooling its resources and then allocating its memory resources to the CXL ports that are connected behind each of those links. How a particular device does configuration of these resources is device vendor specific. In this example, we're showing that it's a 4-ported CXL memory device with equal allocation of pooled resources across those ports. And it's showing each color that is denoting that each of those CXL ports is mapped to a different operating system or VMM image, essentially a different address space. And as you can see, when the host physical address comes in on each CXL link, it's coming from the address that's mapped into a specific host address domain, and the device is going to do a host physical address to device physical address translation. And that host physical address to device physical address translation is going to be very specific to that SLD because it's managing its memory and allocating that memory across different operating systems. A few things to note here is that CXL supports asymmetric capacity allocations. So this example is showing symmetric allocations, but the allocations for a particular device could be asymmetric, and that's supported by the specification. Furthermore, CXL specification adds support for dynamic capacity allocation of memory. This will require Fabric Manager support for dynamically managing resources, platform and kernel level software development for dynamic allocation and management of CXL memory. Now, in the previous example was where you had resources and you divided those resources across each link, which means that a multi-ported device had to have that many links, as many links that it can partition its resources into. Now, a multi-logical device takes a different approach. You have one CXL link coming in, but then you're able to partition your resources behind that one link and allocate those resources to multiple OS images that are connected through a switch to that particular device. So we call this type of a device a pool type 3 device. Architecturally, this device is capable of partitioning its resources into 17 partitions. 16 of those partitions can be used for assigning them for memory, as an example. So it can take all of its memory resources and partition up to 16 logical devices. There is one special logical device that's known as the FM-owned LD, or Fabric Manager-owned logical device. The Fabric Manager-owned logical device, it doesn't allocate any memory resources. It's only used for discovering this link, managing this link, and configuring this device, configuring the device resources, and partitioning it across these memory resources. Now, each logical device is accessed through what's known as logical device ID. So every time a new CXL IO transaction is made to the device, that particular IO transaction is designated with a logical device number. When the request comes in, the device looks at the logical device number, and then it, through that mechanism, understands which logical device the access is coming in, and then services that request. And similarly, each memory request that comes in with a logical device number, so that the device then understands which of those partitions the access is for, and then it maps it to the given logical device as shown in this example. On the right side, we're showing you a device that's partitioned into 16 logical devices. Each logical partition is identified with logical device number 0 through logical device number 15. The mapping of logical device number happens through the switch, and the Fabric Manager is the one that comes in and through an FM API informs the device about how many partitions need to be configured and all of its requirements. When the system boots, each partition advertises the capacity allocated to it using the standard CXL discovery methods. And the operating system running on each of these logical devices identifies what capacity of memory is connected to that logical device and then assigns the specific host physical address. Next, we will go into a little bit more detail on how it is possible to implement pooling. A critical component to this is really about the Fabric Manager connection. The Fabric Manager is a control entity that manages the switch and the memory controllers. It can be an external BMC, an external CPU, or of some sort, or it can be one of the hosts in the system, or it could be implemented with firmware internal to the switch. We do get a number of questions on this topic. The most typical application is really that it's an external processor that's managing a lot more than just the CXL switch, and it has communication to the outside world and a Fabric Manager endpoint. The connection to the Fabric Manager is not required for many CXL systems, but in the cases where you want to support MLD ports as a multi-logical device that has traffic associated with multiple hosts or virtual CXL switches, you must have a Fabric Manager. And if you want to do dynamic moving of resources, whether those are SLD components or memory within either a multi-port or an MLD component, you still need a Fabric Manager to be able to do that. And the CXL switch standard defines the standardized interface called the FM API that is used for the Fabric Manager to communicate with these devices. The interface is actually quite simple and elegant. It's a very low-level command response protocol. It's built on MCTP, and as a result, it doesn't matter what the physical interface is. It could be PCI Express, CXL.io, SMBus, Ethernet, USB, or in some instances where the Fabric Manager is internal, you just have a firmware protocol that passes MCTP packets between them. But in all cases, the commands are the same. The packaging within the MCTP packet is the same, and it's only the physical interface that changes. Another major concern that we had when developing the CXL 2.0 spec is to ensure that the Fabric Manager does not need to be performant. It's not responding to config cycles or memory cycles, so it doesn't need to be a high performance CPU, and you don't need a high performance link in order to make it work. So it's a very flexible system that allows communication between the external controller and the system. We'll go through some of the details on how that works in the next slide. So as I was saying, the Fabric Manager plays a critical role for supporting memory pooling, specifically around dynamic changes. I had earlier commented that for initial configuration, often the Fabric Manager will get involved before the host boots, determine what devices are out there, produce the binding so that once the host boots and does enumeration, it can find the devices that are allocated to it, including logical devices within an MLD. For the rest of this discussion, we're going to talk more about the dynamic changes that happen after boot and some of the responsibilities of the Fabric Manager when you have a resource in the system that is being shared. So if you're talking about an MLD port, the physical port is shared between multiple hosts, multiple virtual CXL switches. One entity has to do the error handling, configuration status monitoring of all of the things associated with it. And in CXL, that entity is the Fabric Manager. Downstream ports connected to MLDs, including their PCI to PCI bridges, are owned by the Fabric Manager, as you've seen on an MLD component, that one of the logical devices is used for configuration only. It does not pass CXL.memory traffic, and it is the Fabric Manager, and it is Fabric Manager owned, so that it can configure the allocations between resources and then unbinding and rebinding of logical devices within an MLD. We know that from the previous slides, a logical device can have up to 16 performance logical devices in it. And each of these can be bound to sync to a single host. Well, it's possible that you could have more than 16 hosts in the system, and a logical device can be moved from one to another. And in the subsequent slides, I'm going to talk about a few examples. And these next three line items are really what I'm going to be covering. The first is reallocation of a single logical device memory controller, a reallocation of memory within a multi-logical device, and the reallocation of memory within a multi-port single logical device. One clarification I wanted to make is that even though a multi-port SLD looks like an MLD, it actually connects as a single logical device, and it behaves exactly like a single-ported single logical device to individual hosts. It's just the management of resources behind it that gets handled slightly differently. So this is similar to the diagram we saw previously. I've just simplified it to have only two hosts in the system. We've got two hosts at the top, and we've got three single logical device memory controllers at the bottom. So these are the non-pool devices, and we've got an external Fabric Manager connected to the switch. In this example, we've got a host that's decided that it no longer needs some memory, and it's going to notify the Fabric Manager that the memory is no longer needed. This communication is part of the CXL standard communication the communication between the host and the Fabric Manager. There are many other standards that are already provide these features, and there's always a connection between the host and the Fabric Manager that's external, so we didn't include that as part of the specification. In this case, we've got the host notifying that it no longer needs device number 4's memory and that it wants it to be freed. Now we have the Fabric Manager that uses the Fabric Manager API to pass the command which is an unbind command. It's going to tell the switch to unbind device number 4 from the virtual CXL switch associated with host number 2. In this case, the Fabric Manager doesn't need to tell the host anything. It's the switch's responsibility, and it's going to use that PCI Express manage hot remove mechanism, which is very well established and easily handled. To request that device 4 be removed, host number 2 will unload the driver, quiesce the traffic, and once the handshake is complete, device number 4 is now completely unbound. At this point, the Fabric Manager could go into device 4, it could do accesses to it, and ensure that either the memory has been wiped in the case where I'm moving it from one host to another, and I don't want to keep any of that additional memory. But it's also possible that host number 2 will I wipe that memory before it relinquish control. So at this stage, device number 4 is free and clear. Its memory has been wiped. It's ready to be moved to another host through another virtual CXL switch. Using a very similar command, only this time it's the bind command, the Fabric Manager tells the switch to bind device number 4 to host number 1's virtual CXL switch. And again, very similar to the previous slide, we use PCI managed hot add. The switch notifies the host that there is a link state change and a presence change. The host comes out and emulates the device, finds out what its capabilities are, configures the HDM ranges in both the switch and the device, and then starts accessing its memory. This is the previous diagram as well, but instead of using SLD components, we're now using MLD components, and we've got a number of memory controllers. And some of the memory has been allocated to the yellow host and some to the blue. And again, similar to the previous example, the host notifies Fabric Manager that some D2 memory is no longer needed. In the previous examples, for example, the single logical device, the Fabric Manager would tell the switch to do the reallocation. In this case, the Fabric Manager sends an MCTP command that is tunneled through the switch to the device. It targets the Fabric Manager owned logical device in the multi-logical device component, and it tells it to do some deallocation of blue memory. This deallocation of blue memory causes the multi-logical device to update its coherent device attribute table, the CDAT, and that update results in an interrupt sent to the host. And the host now knows that its memory is now gone. It can no longer access that memory because the MLD component is responsible for enforcing security and ensuring that a device can't access memory that it hasn't been allocated. And it will update its HDM ranges so that it no longer even attempts to. So very similar again to the previous example. The FM is going to send a tunneled MCTP command to reallocate some of the memory to the yellow host. The CDAT is updated. The device notifies the host. The host comes out and finds out what's changed, updates the HDM ranges, and then starts using the memory. So the important part of this is that no other traffic was stopped while these updates were in progress. None of the traffic from host 1 to device 1, but also none of the traffic from host 1 to its existing location in D2, device 2, or from host 2 to its existing locations in device 2. Traffic keeps moving while we are doing these updates. The only thing that changes is the allocation of this unused memory chunk that's moved from one host to another. Okay, now I'm going to give an example of a system where we have memory pooling without a switch. Prakash had that giant crossbar diagram. I simplified this down to just two hosts, and here you can see the Fabric Manager has an out-of-band connection to the devices. In many cases, it's SMBus, but it could be whatever the devices are supporting. The physical layer interface is not mandated by the CXL spec, similar to the previous examples. The host notifies the firmware that some memory is no longer needed. Device 2 notifies the host that something has changed. The memory is now free. Fabric Manager then sends a new command to the device indicating that host number 1 should now be allocated that memory. Thing to note is that although this looks like an MLD, multi-logical device, it's really a single logical device that has multiple ports and the memory can be allocated between them. Each port looks like an endpoint with its own type 3 memory controller, has its own configuration space, and its own performance parameters. There are a few other Fabric Manager API features beyond what we've seen already. Bind, unbind, and set the logical device allocations that allow the Fabric Manager to do some of the things we need to do in order to make memory pooling possible. First is switch discovery at boot time. We want the Fabric Manager to be able to come out, find out what the switch capabilities are, how many VCSs it supports, and what are the connected devices when they boot, what they're advertising, what they are linked up with, all the things necessary to understand what's connected, and allow it to do the bindings at the initial stage. The switch is responsible for event notifications, switch link events, advanced error reporting, anything associated with control or status that relates to Fabric Manager owned resources, or resources that the Fabric Manager may not own, but it still needs to have information about. Then lastly, things like the type 3 memory controller we mentioned earlier, the quality of service parameters, the things that allow for bandwidth latency characteristics, and that result in the memory controller giving information back to each host as to what those characteristics are. And the FML API allows all of these things to happen. So we've covered a fair amount of ground here on how memory pooling is supported using CXL. We've gone through how we can essentially perform disaggregation, have a giant pool of memory. We can allocate it to individual hosts or individual root ports, and we can dynamically change it. It's extremely powerful, and these are the systems that are getting built today. It supports dynamic allocation and deallocation. Where all of this amounts to is big savings and a total cost of ownership. As you can see from the discussion today, CXL attached memory use models continue to grow from direct attached to realizable memory-centric computing. CXL Consortium continues to address the challenges to support CXL attached memory. Large opportunities lie ahead for the ecosystem. Call to action, get involved with the ecosystem. Your contributions will be very valuable in enabling this technology. Thank you for your time. Prakash and I are ready for any questions you may have.
Hey, thank you, Rob and Mahesh and Prakash for this, excellent presentation on memory challenges and memory attach. Let's go to some questions. Can we have both of them on? Okay. All right. Thank you. So Prakash, perhaps this is a question for you. So there's a number of questions around page migration. So I'm just going to ask them first. If you want Mahesh to take them, just pass that on. So the first question is from Alan Baum. For allocating hot, cold memory between CXL and local memory, what is the granularity? Is it standard page-based? Oh, can you hear Prakash?
Can you hear me?
Yes, I can. Did you hear my question, or should I repeat it?
No, I heard the question. So yeah, it is page-based because smaller granularities would take up too much compute, and there is not operating system methods to keep track of those. But I posted the link for our TPP paper and the source code in the Slack channel. So you guys can take a look at the paper to get more details on implementation.
Thank you, Prakash. The next question is from Yashwardhan Ravne from NVIDIA. Is the watermark for promotion and demotion the same, or are they different? And can you give some color on how this is determined?
Yeah, so I think the original Linux implementation had a single watermark. And because it takes time for you to reclaim memory, the memory fills up much faster than you can reclaim. And so one of the things that was done in this work was to have a lower watermark for reclamation, or rather you start reclaiming much more sooner than you really need to. so that you can keep up with the way the memory gets allocated. So you always have room in your, so this assumes that your hot set can fit in local DRAM. And so whatever gets hot can be placed in local DRAM.
Thank you, Prakash. Let me ask this question to Mahesh. This is a question from Sabarish Ravikumar from Waymo. How do you avoid blackout period when they are being promoted and demoted?
I think when you do get to those regions for accessing that particular memory, you are going to go through some of those periods. I think Prakash has a link to the TPP paper that does describe some of those mechanisms. Prakash, you want to add anything to that?
Yeah, so I think one thing that they did with TPP was instead of taking a page that has become cold to a swap device, you directly move it to CXL, which means a smaller hit than it would normally be if you were reclaiming a page. So that's one instance example, but you can read the paper for more details.
Thank you. So the next question is from Jose Monsalve Diaz from Oregon National Labs. Can you expand on what are the performance gains you're seeing in real applications from using the hot-cold replacement policy?
Yeah, so I think over standard Linux, we've seen up to 20% improvement. And from some of the auto-NUMA and NUMA balancing, we still see 12 to 18% performance boost with TPP, with the applications that have been discussed in the paper.
Okay, thank you, Prakash. So this has to be the last question, again from Jose Diaz. Can you explain why the Fabric breaks the possibility of using Type 2 devices as PIM?
Yeah, I think I answered this in the Slack channel, and this is probably better answered by folks in the protocol side. But basically, a PIM device is going to look like a Type 2 device. And currently, the CXL3.0 Fabric does not allow sharing of Type 2 devices. You could still have like a fully owned Type 2 device that's fully owned by a single host under the Fabric. And maybe somebody else can answer this better, if Rob or someone else is.
Yeah, we probably cannot get them on. But what we'll do is, Jose, we'll get back to you on this one and probably update the Slack channel after the tutorial. Thank you. Thank you, Prakash and Mahesh. We'll move on to the next session. Okay, so the final tutorial session focuses on CXL3 Fabric features. Tony Brewer from Micron will review many of the new features related to memory fabric and global fabric attached memory. This has garnered a lot of interest, and Tony will also go through motivation and use cases. Tony Brewer is currently the chief architect in Micron's near data computing group. He is the principal investigator on multiple government contracts and leads a team of architects and researchers focused on fabric attached memory with near data computing. His career has been focused on system architecture in both high-performance computing as well as the telecommunications industry. Tony Brewer received his BS and MS degrees in computer engineering from Purdue University and has over 175 filed patents. Let's go to the session.
Hello, my name is Tony Brewer, and I will be the presenter for this fourth and final session of the CXL tutorial workshop. The title for the presentation is CXL3 Fabric Introduction and Use Cases. The agenda for this session starts off with motivation and use cases for the CXL3 Fabric. This is from a marketing perspective. The next topic is why CXL 3.0 Fabric. This is more from a technical perspective. Then we discuss the topics CXL3 Fabric Basics and Scope, port-based routing, GFAM device transaction flows, host address map, address interleaving, device media partitions, GFAM device media partition access protection, and finally a summary. The motivation for CXL3 Fabric comes from the explosive data growth, often referred to as big data. The data comes in the form of social media, healthcare, smart cities, and IoT, with the majority of this data being sensor generated. The result is a requirement for data to be stored and analyzed continuously. This data volume and velocity demands large clusters for timely analysis, and today using Ethernet or InfiniBand networking. These types of systems require significant power to move and copy data between the connected hosts. As a result, there is a need for an efficient, low latency, and high bandwidth solution, which minimizes this data movement. The applications perform the analysis may be in the areas of artificial intelligence, high-performance computing, and high-performance data analytics. In the AI space, an example application is machine learning parameter set training. This application requires large training sets that must be periodically accessed with large numbers of processors or accelerators to iteratively optimize training parameters. The size of the AI networks and associated parameter sets continues to grow, resulting in very large clustered systems with high inter-system bandwidths and memory requirements. Systems based on CXL3 fabrics will provide scalable, heterogeneous compute and memory capacity, enabling tight integrations and allow efficient processing. A second example is in the HPC space is the oil and gas exploration field. The application is called time reverse migration and is used for modeling wave propagation velocities through the ground. The algorithm uses three-dimensional stencil code to approximate a wave propagation equation. The size of the three-dimensional grid grows with the refinement of the model, allowing increased visibility for the analysis. Similar to machine learning training, reverse time migration uses large clustered systems due to the huge computation needs and often uses GPU accelerators to perform the calculations. Communication between the clusters is one of the bottlenecks of the algorithm that can be addressed by the CXL3-enabled scalable heterogeneous systems. A final example is in the area of high-performance data analytics. The application example is graph analytics. Graph analytics is becoming used increasingly in more fields to understand the relationship between objects within the graph. Graphs are commonly referred to as having unstructured data, generally meaning stored in non-tabular data structures. The result is that graph analytic algorithms frequently make use of accessing small-sized references to memory. The shared global address space with load store semantics will provide an efficient platform for applications with these characteristics. The slide shows a CXL3 Fabric use case topology. The diagram shows multiple hosts and multiple GFAM devices interconnected with a CXL switch fabric. The hosts are two-socket server with memory DIMMs and directly attached CXL memory devices. Each host is an independent domain within the overall system that is able to share data within the GFAM devices. The expected latencies for the system are shown in the lower left of the slide. Latencies are shown for 3 tiers of memory within the system. The first tier is referred to as local scope. This is defined as DRAM on the motherboard. Here the latency is expected to be sub 100 nanoseconds. And of course, this is load dependent for the system. The second tier is referred to as system scope. System scope is defined as a local direct attached CXL memory, normally within the same chassis as the host processor. This tier is expected to have sub 200 nanosecond latency. So this will be the capacity tier for a host processor with greater capacity and increased latency than the local scope. The final tier is referred to as rack scope. Rack scope is defined as the disaggregated global memory within a rack. It is this scope that the CXL3 Fabric is largely focused on providing. This tier is expected to have sub 600 nanosecond latency. This tier will be the capacity memory for the overall system supporting sharing of the data across all processors within the system. Systems of this type with multiple tiers of memory will require application writers to be aware of data placement to achieve the potential benefits of the global shared memory. An application writer will have multiple options as to how to mitigate the effects of the longer latency to fabric-attached memory. The first option is to aggressively use processors' prefetch instructions. This may be effective in algorithms requiring low fabric-attached memory bandwidth. But for algorithms requiring high fabric-attached memory bandwidth, the number of outstanding requests from a processor to cover the expected fabric-attached memory latencies will exceed that supported by most processors. A second option to an application writer will be to move the data from the fabric-attached memory into the private memory of a processor. A dedicated data movement engine with sufficient outstanding requests to cover the latency to fabric-attached memory will be required to make this an effective option and are expected to be available for this purpose. This data movement will typically be from the rack scope fabric-attached memory to local scope DRAM close to the processor memory. Ideally, the local scope DRAM memory is HBM memory, providing very high bandwidth with reduced latency as compared to standard DRAM on DIMMs. The third option for mitigating latency to memory is with the memory-centric computing, as described on the next slide. Memory-centric computing is expected to play a big part in future disaggregated memory systems. An example that highlights the need is AI training on large training data sets with billions of training parameters. These training runs today can take multiple days on large clusters, consuming tens of kilowatts of power. The majority of the power consumed can be attributed to data movement, not the actual computation. Memory-centric computing moves the compute to the data, eliminating a significant amount of the power consumption. The diagram shows a CXL3 fabric with host and accelerators on the top, and GFAM devices with near-memory computing on the bottom. Each accelerator in the diagram is tightly coupled to a host. For highest efficiency, the accelerator needs to operate, for the most part, on data directly connected to its host. Similarly, compute can be moved to a GFAM device to be performed on its near-memory compute capability. Compute within a GFAM device is advantageous in that the GFAM device holds the primary capacity memory for a large shared memory application. Performing the compute in the GFAM device eliminates moving the data outside the device and as a way of mitigating the increased latency of a host accessing GFAM memory. The mechanisms to support near or in-memory computing in GFAM devices are not defined in the current release standard, but is expected to be addressed in future ECNs or specification releases. As stated earlier, memory-centric computing is expected to play a big part in future disaggregated memory systems. We talked about the market need for large, scalable systems. This slide presents the technical need for the CXL 3.0 fabric as compared to what was defined in previous versions of the CXL specification. CXL 2.0 mechanisms scaled to 16 hosts using logical devices per CXL memory device. CXL 2.0 targeted memory pooling and sharing within relatively small system configurations. CXL 3.0 extends these capabilities and introduces scalable mechanisms to support much larger systems, allowing hundreds of hosts, accelerators, or NIC devices, and thousands of memory devices supporting petabytes of memory. These systems will scale to the rack and pod level to address the big data application needs, as well as the composable system space. Some of the extended capabilities include extended switch topologies, enhanced coherency capabilities, global shared fabric attached to memory, and peer-to-peer resource sharing. These capabilities, as well as others, will be described in this presentation. CXL 3.0 is the first step towards standardizing the scalable, multi-host system space. This specification defines the fundamental concepts of the fabric, but many areas are in various phases of definition and are not ready for release. These areas include fabric management, security, reliability, to name a few. Future ECN and specification releases are planned to address areas where standardization will be valuable for the industry. This slide presents the foundational concepts for the CXL3 fabric. The diagram shows a system using leaf spine fabric topology with a number of edge ports connected to NIC, CPU, accelerator, memory, and GFAM devices. The most basic concept for CXL3 fabrics is packets are routed based on port identifiers. The packet source port is identified by a source port ID and a packet's destination port by a destination port ID. Contrast this with CXL2's hierarchical-based routing, where a packet source is the root port of a virtual hierarchy, and the routing is conceptually accomplished by address range comparisons throughout the switch fabric. CXL3 provides 12-bit port identifiers, allowing up to 4096 fabric edge ports. Each CXL fabric edge port is assigned a unique port identifier. These unique port identifiers allow CXL3 switches to route a packet using table lookup at the various switching points throughout the fabric. The 12-bit destination port identifier is used as the index when performing the table lookup. Global Fabric Attached Memory Devices, referred to as GFD, are scalable memory resources. They are accessible by all host and peer devices within the cluster. The global FAM devices support load store memory semantics. These semantics allow hosts and peer devices to access the shared memory content in 64-byte memory line sized accesses, supporting normal host caching mechanisms. Support for multi-level switches with port-based routed fabrics provides additional capabilities for building software composable systems. In the above figure, a leaf spine switch architecture is shown with all resources attached to the leaf switches. Each domain may span multiple switches. Cross-domain traffic is limited to CXL.mem and CXL.io using unordered I/O transactions. For multi-switch topologies, composing systems from resources within a single leaf switch allows for lowest latency configurations. In such configurations, a spine switch is only used for cross-domain and GFAM accesses. High-radix switches will have high value in composable systems due to this low latency for single switch domains. CXL3 introduces the concept of port-based routing. Previous versions of the CXL specification only supported hierarchy-based routing. CXL3 augments this capability with port-based routing. A CXL3 compliant switch has the ability to route packets using both hierarchy and port-based routing. One aspect that a system integrator must be aware of is the interoperability issues when mixing use of CXL2 and CXL3 switches within a switching fabric. The figure shows system configurations that interconnect hosts, one or more switches, and endpoint devices. Note in the diagram that switches are labeled as HBR, indicating a CXL2 compliant switch without port-based routing capability, and PBR, indicating a CXL3 compliant switch that does support port-based routing. The basic rules are: a host root port may be connected to either a hierarchy or port-based routed switch upstream port. The first row of configuration show the host connected to a port based on routed switch upstream ports, and the second row shows hosts connected to hierarchy-based routed switch upstream ports. A device may be connected to either a hierarchy or port-based routed switch downstream port. The configuration shows devices connected to downstream ports of both hierarchy and port-based routed switches. A port-based routed switch upstream port may be connected only to a host root port. Connecting to a hierarchy-based routed switch downstream port is not supported. The lower right example illustrates the case that is not supported. the case there with the red X on it. A downstream port of a hierarchy-based routed switch is connected to an upstream port of a port-based routed switch. So that configuration is not supported. The fourth rule is an HBR switch upstream port may be connected to a host root port, a port-based routed switch downstream port, or a hierarchy-based routed switch downstream port. Essentially, there are no issues of what a hierarchy-based routed upstream port can be connected to. And finally, a GFAM device may only be connected to a port-based routed switch downstream port. This connection is shown in the upper left configuration. The functionality of a GFAM device requires receiving a source port ID to index into various structures for request processing. A hierarchy-based routed switch would not provide the source port ID, causing the interoperability problem there. In summary, the mixing of hierarchy and port-based routed switches is supported, but care must be given to ensure that the CXL-defined configuration limitations are followed. CXL3 Fabric has introduced the concept of inter-switch links. The previous versions of the CXL standard allowed switches to be interconnected, but required two independent links between the switches. A switch would connect an upstream port to one link and a downstream port to the other link. The figure on the right shows the message classes and subchannels that traverse the link. Note that the full set of classes and subchannels are provided in both directions across the interface. The CXL3 defined interswitch link allows better bandwidth link utilization and fewer ports to be used for interswitch configurations, allowing fabrics with larger radiuses to be constructed. One aspect of interswitch links that has not been yet addressed by the CXL Standard Consortium is how multiple links between the same pair of switches is to operate. Some traffic classes have ordering rules requiring the use of the same link for a specific address. These include CXL.mem and CXL.cache. Other traffic classes were defined specifically to avoid forced ordering. An example is the CXL.io unordered I/O subchannel. Traffic without ordering rules could be transferred on any of the interswitch links, allowing load balancing between the links. As stated, the CXL standard does not define how multiple interswitch links between pairs of switches are to operate. At this point, it is unclear if this is an area for standardization or supported by vendor-defined mechanisms. The slide shows an example port-based routed mesh topology. The system shown in the figure allows a host or peer device to access any device with one or two switch hops. Mesh topologies such as this are common, but introduce the possibility of circular dependencies resulting in system deadlocks. These circular dependencies can be avoided with careful programming of the port-based routing tables within the switches by the system fabric manager. A system as shown in the figure could be assembled in a rack as 4 chassis, where each chassis consists of a host CPU, a CXL switch, and multiple CXL device slots. The chassis could be interconnected with either copper or optical links. Today's standard 2U 2-socket chassis would be a cost-effective way to scale a system, providing shared memory across the hosts using global fabric attached to memory. Larger systems could be constructed where each of the chassis are a quarter or even a half a rack. These larger systems would require higher radix switches, but would provide the same maximum of 2-hop switching and latency profile as the smaller 2U-based system. The CXL fabric will allow cost-effective scale-up systems to be constructed from standard off-the-shelf components. A GFAM device is accessed using either CXL.mem or CXL.io using the newly defined unordered I/O subchannel. Generally, CXL.mem is used by a host to access GFAM memory, and CXL.io is used by peer GFAM devices to access GFAM memory. Next, I'll describe the steps for handling a host-generated CXL.mem GFAM memory request. The request starts from the host using the CXL.mem message class with the master to subordinate subchannel. A switch ingress edge port receives the request packet and decodes the address to identify the target. The destination port identifier associated with the target port, the source port identifier associated with the ingress port, and the original CXL.mem packet are used in generating the port-based routing FLIT. The FLIT is routed through one or more switches until it arrives at the target destination port. At the destination switch edge port, the FLIT is forwarded to the target device. Note that for a GFAM device, the FLIT is forwarded to the device with the source and destination port identifiers. For CXL 2.0 compliant devices, the PBR FLIT is converted to the expected non-PBR FLIT format prior to forwarding to the target device. The target device performs address normalization, that is converting the received host physical address to the local device physical address, and performs access protection checks to ensure that the source host has the access rights to access the addressed memory location. Once the received address is normalized and access protection is checked, then the requested memory access is performed. The response path starts with the device generating a response FLIT in native port-based routing format. The port-based routing FLIT uses the request's source port ID as the response FLIT's destination port ID and the current device's port ID for the response FLIT's source port ID. The response FLIT is sent to the switch fabric port, and the destination port ID is used to index into the routing table to determine the path to route the FLIT to the switch fabric destination egress port. The fabric destination egress port converts the port-based routed FLIT to the CXL 2.0 defined CXL.mem hierarchy-based routing FLIT format by dropping the source and destination port identifiers. The FLIT is then sent on to the host. Note that the port-based routed source port processing of CXL.io, CXL.mem, and CXL.cache transactions are still being defined and will be delivered in a future specification ECN. CXL 2.0 supported host and accelerator data sharing through a device memory bias mechanism. This supported a one-to-one host and accelerator sharing model with limited additional capability. CXL 3.0 introduced the back invalidate flow, which supports inclusive snoop filters and peer-to-peer memory requests. An inclusive snoop filter tracks the coherency state of memory lines that are being held in the caches of all hosts. CXL 3.0 back invalidates supports an accelerator or peer GFAM device to access memory on different GFAM device and, if needed, issue a request to a host that has a line cache to give up ownership of the line. Previously, this capability, using the CXL 2.0 defined mechanisms, had the potential for deadlock due to sharing of subchannels. CXL 3.0 eliminates this deadlock potential. The figure shows the transaction flow of an accelerator accessing a GFAM device that requires the back invalidate to obtain the addressed memory data. The flow starts with the accelerator issuing a CXL.io unordered I/O memory request to the GFAM device, shown as packet flow number 1 in the figure. The GFAM device searches the snoop filter to determine if a host has the line cached. If the line is cached, and in the exclusive state or in a shared state and the CXL.io unordered I/O request is for a write, then the CXL.mem back invalidate must be sent to the owning host. This is shown as a second packet flow in the figure. The host checks its cached and, depending on the state of the line, may need to perform a write of the dirty data back to the GFAM device, or as shown in the figure, may be able to just invalidate the cached line and provide a back invalidate response back to the GFAM device. Packet number 3 shows the shows the back and validate response packet. Finally, with the memory line coherency resolved, the GFAM device can send the CXL unearned I/O response back to the accelerator. This is shown as packet flow number 4. The CXL 3.0 back and validate flow provides the ability for full system sharing of GFAM memory lines and is one of the key capabilities enabling GFAM memory sharing. This slide discusses the CXL3 host physical address map. As shown in the figure, each host has some private local memory. This memory is generally mapped into the lower address range of the host physical address map. The map is constructed by the boot firmware and populated, at least partially, by the PCIe discovery process. The PCIe discovery process finds the local direct attached CXL3 devices and maps the media into the host physical address space. At the top end of the host physical address map is where MMIO space is mapped. As with direct attached CXL memory devices, the PCIe discovery process finds all PCIe and CXL devices and maps their associated MMIO space into a host physical address map. Between the local memory and local MMIO spaces is the fabric address space. The fabric address space is a contiguous range starting at fabric base and extending to fabric limit. Each host may map the fabric address space into a different host physical address range. This allows each host to execute low-level boot firmware without interaction with other hosts. The fabric address space is subdivided into segments. Each segment is mapped to a GFAM device. Note that it is acceptable to map multiple segments to a single GFAM device. This may be a common practice to handle some GFAM devices with a small capacity memory, such as possibly DRAM, and other GFAM devices with large capacity, such as storage class memory. A host does not need to be aware of segments. Rather, the ingress port of a CXL switch must have the ability to identify which segment a GFAM reference belongs to and route the request appropriately. The previous slide discussed the fabric address range segments within a host's physical address space. This slide discusses the mechanism at the ingress port of a CXL switch that processes the host physical addresses and determines which GFAM device, represented by a destination port ID, the request should be routed. The mechanism first performs a range check to determine if the host physical address is within the fabric address range. Those requests that are in the range are then processed to determine which segment within the range the request belongs. Note that segments are defined to be a power of 2 in size, and the fabric address range is aligned on the largest segment size power of 2 boundary. The result of these two requirements is that to determine the segment from a fabric address range is a matter of picking the appropriate bits out of the host physical address. The segment identifier is used to index into the fabric address segment table, referred to as the FAST table. Each table entry specifies the interleaving that is to be performed, and as a result, an index into the second table that provides the destination port identifier. The second table is called the interleave DPID table. Once the CXL switch ingress port determines the DPID for the request, then the request can be formatted as a FLIT with the source and destination port identifiers. The FLIT is then routed to the destination port through the CXL fabric. This slide shows a simple memory interleaves example. The figure shows 2 hosts, a single switch, and 4 GFAM devices. Memory is interleaved across the 4 GFAM devices and is an interleaved set. A host may interleave across its root ports on any interleave granularity. The only restriction is that each specific memory line must be handled by the same root port for each request. The switch ingress edge port will decode and interleave requests to the target GFAM device port. The switch decodes and interleaves requests based on the mechanism described on the previous slide using the FAST and IDT tables. Once the request is routed to the target device, the device normalizes the host physical address to the device physical address. The device maintains knowledge of the number of GFAM devices in the interleaved set to support the address normalization. A more complicated interleaving example is shown on this slide. Here we have 4 independent switch planes commonly used to provide more fabric bandwidth. Each host has 4 root ports that connect to the 4 switch planes. These 4 root ports provide the first level of interleaving. The interleaving is set up to be on 4K page granularity, with the hosts using address bits 12 and 13 to determine which root port to send a request and thus which switch plane will receive that request. Each switch plane performs a second level of interleaving using request address bits 14 and 15. The end result is that 4K pages are interleaved across 16 GFAM devices with significant overall bandwidth increase for access to the specific range of memory. GFAM device interleaving will normally provide higher application performance by spreading the accesses of the memory region across multiple devices, thus providing higher overall bandwidth to that region and avoiding memory hotspots. However, there are situations where memory interleaving may not be advantageous. One example is when near memory computing within a GFAM device is being leveraged. In this case, the interleaving of a memory region may cause significant peer-to-peer traffic requirements, causing suboptimal application performance. System software will need to provide options to allow application writers to optimize the overall system interactions. This slide introduces the concept of a GFAM media partition and how a media partition is mapped into a host physical address. A GFAM device may support multiple device media partitions, referred to as a DMP. The fundamental attribute of a device media partition is the media type. Common media types are volatile and persistent. A GFAM device may support multiple host decoder regions per host. Each decoder region may map a portion or an entire device media partition. The figure on the right shows the mapping from a host physical address on the left to the device media partitions on the right. As previously described, a GFAM region of a host's physical address range is subdivided into segments. Requests to the address range covered by a segment is routed to a specific GFAM device as configured by the Fabric Manager. At the GFAM device, the per host GFAM address decoders map portions or all of a device media partition into the host physical address range. These GFAM address decoders translate from a host physical address to the common device physical address. Depending on the overlap of different hosts' GFAM address range decoders, determines whether a region of device media partition is exclusive for a single host or shared between multiple hosts. This slide describes the mechanism used to transform host physical addresses received by a GFAM device to local device physical addresses. Each host may map the Fabric address range into a different location within their host physical address map. As a result, on each GFAM device, source port identifier specific information is needed to perform the translation. This information is provided by the GFAM device decoder table, referred to as the GDT table. Within the GDT table, for each SPID, up to 8 address ranges can be mapped to device physical addresses. This flexibility allows a host to map a device with multiple device media partitions into different ranges in its host physical address space. This may be particularly useful if the multiple device media partitions include different media types with different characteristics. The received request's host address is compared in parallel across 8 address ranges for a match. If no match is found, then the request is dropped. A timeout will be detected. When a match is found, the first step is to use the information in the table to remove the host physical address bits used for CXL device interleaving. The GDT table entry specifies a field named GRAN that specifies the interleave granularity. The granularity can be specified from 256 bytes up to 16K bytes with all powers of 2 within the range allowed. This field indicates the lower bit of the range of bits from the received host address that must be removed. The GDT tables entry also provides a field named INTLV that specifies the interleaving ways for a memory region. Interleaving ways may be set as interleaving disabled or in the range of 2-way to 256-way, again with all powers of 2 within the range allowed. This field indicates the number of bits in the received host address that must be removed. With these two values, granularity and interleave way, the interleave bits can be removed. Once the bits are removed, then the host physical address base is subtracted off, leaving a physical address offset. Finally, the device physical address is generated by adding in the device physical base address. As stated, this mechanism supports up to 8 separate host physical address regions per source port to be mapped to device physical address regions. CXL3 Fabric provides access protection mechanisms to ensure that a host is not allowed to access GFAM memory other than where the Fabric Manager has enabled it. This is an important feature, ensuring that a host system with misbehaving system software, through software bugs, software security holes, or other malicious means, cannot corrupt data stored in GFAM memory belonging to other hosts. The protection mechanism are provided in 3 different system locations. First, a host processor translates an application virtual address to a host physical address. If virtualization is being used, then the translation occurs through an intermediate physical guest address. This translation occurs through the use of the processor's memory management unit, with access protection occurring on the supported page granularities, commonly 4K byte, 2 megabyte, and 1 gigabyte page sizes. An invalid virtual address causes an address translation fault, and on Linux, the issuing application is either terminated or sent a signal if enabled. The second location access protection is provided is at the ingress port of the CXL switch. The ingress port contains the Fabric access segment table, which is used to determine the target CXL Fabric port for each FLIT. As previously discussed, the host physical address space contains a contiguous region that all GFAM memory is mapped, referred to as the Fabric address range. This address range is divided into a number of equally sized segments, with each segment mapped to a GFAM device. An ingress port's Fabric access segment table contains a valid bit per segment to identify requests with invalid host physical addresses. Requests with invalid host physical addresses are dropped, causing the request to timeout. How a host processor handles a detected request timeout is not defined by CXL. Finally, the third location that access protection is provided is within the GFAM device through the dynamic capacity mechanism. This mechanism is described on the following slide. This slide presents the global FAM device dynamic capacity access protection mechanism. Each global FAM device may have multiple device media partitions, with each media partition divided in a number of blocks. Each block is assigned a memory group identifier. The defined mechanism accomplishes the protection check through use of 2 tables. The first table, the source port ID access table, referred to as the SAT table, translates from the request packet source port identifier to a bit vector of accessible device media partition blocks. The second table, referred to as the memory group table, is used to determine the memory group for each device media partition block. Once these two tables are accessed, then the memory group identifier is used to index into the memory group access vector. The resulting bit determines if the access is valid. A request resulting in an invalid access will result in the request being dropped. The dropped request will result in the issuing source port observing a request timeout. Note that with normal system operation, virtual address translation faults detected by a processor's memory management unit are expected. However, timeouts due to the CXL switch and GFAM device access protection checks should not occur. These protection checks will only occur with misbehaving system software. And finally, the summary. Storage and compute requirements continue to grow. CXL3 enables a scalable rack-scale memory fabric. We are just beginning this journey towards a realizable memory-centric computing, and large opportunities lie ahead for standards-based rack-scale compute, and we believe that the chiplet ecosystem, represented by UCIe standard, will be a large part of systems going forward. So please, get involved. Thank you.
Thank you, Tony. Do we have Tony on? All right. A couple of questions for you, Tony. The first one is from KH Kim from IBM. It's from a previous session, but it's probably relevant. Are processing in memory features supported in CXL or planned to be supported in the future? So until Tony comes on, maybe I can just answer the question. Tony already said this in his presentation. We will be supporting PIM features, and it's actively being worked on in the consortium. So either in the 3.1 spec or the next spec will support PIM-related processing. Tony, are you? All right, Tony, I'm going to read out the next question. Maybe I'll type it in for you. What coherency models are supported by the CXL3 Fabric?
So certainly, CXL defines the Type 2 device, which provides accelerators in a system with where the device also has memory. And so those accelerators could be processing memory or processing near memory. However, today in GFAM devices, the CXL 3.0 specification does not provide support for that capability for GFAM. And it is, this is one of the areas beyond the fundamental capabilities supported currently. And certainly it's my expectation, my hope that it is defined going forward for GFAM.
Right. Hopefully you can hear me now. So there is a possibility to use CXL.io and use a driver or an MMIO-based mechanism to dispatch work.
So next question, what coherency models are supported for CXL3 Fabric? So CXL3 Fabric defines support for two coherency models, hardware-based coherency and software-based coherency. For the hardware-based coherency, that's essentially as you would expect, you have a private owner, and then you also have a sharing list per host, such that if a CXL device, a host comes in and wants to gain private access to it, you could use a sharing list and through the backend validate mechanism, clean up the coherency and provide a host private access. Now, the challenge is that as your systems scale, as I said, you can have up to 4096 port IDs for CXL3 Fabric. Scaling to that size where you have potentially hundreds of hosts would make your sharing lists very large. That has, multiple challenges. One is that the amount of coherency state within your CXL device per line grows, huge to the extent that you may end up having as much coherency state as you have data per line, which is prohibitive. And secondly, if you were to go out and invalidate all those processors, you would have a tremendous amount of traffic load on your fabric. And so The CXL3 Fabric has defined support for both hardware and software-based. And for software-based, the CXL device, the GFAM device, does not maintain which processor has it for read-write capability or support, but rather the hosts take responsibility for flushing and invalidating their caches at the right point in time to maintain that coherency across the system. So there are those two different mechanisms, and depending upon your system integrator, how the devices have been designed, the scale of the system, that will all factor into what direction that individual systems integrator will decide to go.
Thank you, Tony. Please give a virtual round of applause to all our presenters today. And thank you, audience, for being patient, working through all the technical difficulties. Once again, a big thanks to the organizing committee, and this includes our tutorial 1. Thank you very much.